we hear critics all the time say, well, the gold standard of science is making testable and falsifiable predictions and testing those predictions and confirming them. And they'll say Cretaceous don't do that. But from your presentation, from what you're saying here, no, Cretaceous have made many testable predictions. Many have been confirmed. For example, yes, the helium and zircon crystals, the diffusion rate.
And I also predicted.
Welcome to Standing for Truth. My name is Donny Budinsky, and this is Sam. We are your hosts for this valuable program. Tonight, we're diving into one of the most controversial and important topics in all of science and faith: the reliability of radiometric dating and what it really reveals about the age of the Earth. For decades, radiometric dating has been held up as undeniable evidence of deep time, that the Earth is billions of years old. But what if the very methods used to claim vast ages contain fatal flaws? What if the evidence, when examined, actually confirms the biblical timescale of a young Earth?
So joining us tonight is someone who has spent decades studying this very question. Dr. Andrew Snelling, PhD in geology from the University of Sydney, a researcher, an author, a director of research for Answers in Genesis. Dr. Snelling has been on the front lines of radiometric research, including his work on radiohalos, isochron dating, and the RATE project, research that challenges the foundations of an old Earth itself.
We're going to be examining why radiometric dating isn't the unshakable evidence it's made out to be, how the data actually points to catastrophic processes during the flood, and why a young Earth remains the most consistent explanation of the evidence. So get ready, grab your Bible, grab your notebook, because tonight we're dismantling dating methods and confirming the truth of God's word right here on Standing for Truth. Dr. Snelling, it is an honor to have you with us here tonight, brother. How are you doing?
All right. Thanks, Donny and Sam. It's good to be with you.
Oh, it's our pleasure. I know we've got a lot to discuss. You have a lot to present, and we like these kinds of comprehensive programs. And so unless there's anything that you wanted to add, Dr. Snelling, in terms of introduction, we could start to move into your presentation.
Yes, I'll just make a comment that, and I'll make it during the presentation, that particularly in the early part of the presentation, a lot of the examples I'm going to use are actually documented in the secular, conventional scientific literature. So it's not as if this is all my work. I'm actually referring to the geochronology literature.
That's one of the numerous things that I appreciate about your work and your engagement on this topic of dating methods in the age of the Earth, Dr. Snelling, is watching so many of your lectures and reading so much of your material on this issue. Is you address it or you debunk it largely right from the conventional literature. It's what a lot of these things is what they're saying, as the audience is going to see shortly.
That's true.
Okay, well, I think we're ready to get into it, Dr. Snelling. And so for those watching, for those enjoying this, the structure of this program, this podcast will be a comprehensive presentation from Dr. Andrew Snelling, followed by some questions and discussion with all three of us. Sam and myself have some questions, and I'm sure the presentation will generate quite a few questions. And then we'll start to wrap things up at that point. And so, Dr. Snelling, let's hand it over to you. Whenever you're ready, we can get into your talk.
Here we go. The first question I want to ask people is, how was the Earth dated? Because most people think geologists have measured the age of the Earth with radioactive dating methods dating of Earth rocks. And therefore they believe that using that method, proven that the Earth is 4.57 billion years old, give or take. But the issue is that the Earth's claimed age was not derived from Earth rocks. I mean, most people think that it was, but that's an astounding revelation. The Earth's age was actually derived from radioactive dating of a group of meteorites. And so here's the isochron age for the Earth based on a group of meteorites. This was done back in the over 70 years ago at Caltech, and it hasn't changed since. And the problem is that it's assumed that those meteorites represent the Earth when it was formed, and that's based on assuming how the Earth and the solar system were supposedly formed. It's based on an assumed evolutionary history. That is, that the Earth and the solar system came out of the solar nebula. And then that assumed evolutionary history is then used to prove that evolutionary history. Voila, we've got this age for the Earth, and it matches the meteorites and the solar system, and therefore that evolutionary history is correct. Well, of course, that's circular reasoning. Now, underpinning this whole dating of the Earth is, of course, the radioactive dating methods. And so we need to dive into those and work out and look at how they operate, how they're used. And so let's try and do some basic teaching on the radioactive dating methods. So some elements, such as carbon and uranium, have isotopes, that's varieties of carbon, varieties of uranium. Carbon has 3 isotopes. Regular carbon is carbon-12. Uranium-238, it has a lot of extra particles in its nuclei. It becomes very unstable, too many neutrons. And so they eject some of those subatomic particles, typically neutrons, from their nuclei so as to become stable atoms. And that's what it involves. The process is called radioactive decay. The decaying atoms are known as radioactive isotopes, or simply radioisotopes. And when these radioactive atoms or radioisotopes of one element decay, they result in a stable atoms of a different element. So uranium will decay eventually to lead. Carbon-14 will decay to nitrogen-14, and so it goes on. So the decaying atoms or radioisotopes are sometimes called the parent atoms, and the resultant stable atoms are called daughter atoms. Parent gives birth to daughter, simple terminology. So uranium eventually gives birth to lead atoms. And minerals, rocks, and fossils contain some of these radioactive parent atoms or radioisotopes and the daughter atoms. So here are the major methods that are used, and we'll deal with carbon-14 later on, but if you hear anyone say that carbon-14 dating has proved that the rocks are millions of years old, if you hear someone say that, you know automatically they don't know what they're talking about, because carbon-14 is never used to date rocks at millions of years old. It cannot date rocks at millions of years old, as we'll learn later on. The principal methods used for dating rocks are uranium, and there's two isotopes of uranium, 238, 235, give different N-member lead, daughter lead atoms, potassium to argon, rubidium to strontium, and samarium to neodymium. Now, you might not have heard of samarium and neodymium. They're rare earth elements, and in fact, neodymium is very important. That's why there's a lot of political fight over rare earth critical minerals at the moment. Neodymium is used in magnets to make them stronger. So they're in magnets in wind towers. Neodymium is used in cell phones, and so it goes on. That's why you may not have heard of that element. Okay, so how do these methods work? A rock is chemically tested for these parent and daughter atoms. You measure how many parent and daughter atoms effectively are in the rock you're testing. And then if the rate of radioactive decay has remained constant at today's measured rate, then we can calculate how long it took for the measured amount of daughter atoms to accumulate from the parent atoms. So if we've got X number of parent atoms and Y number of daughter atoms, we know the rate of decay, then we figure out how long it took for those Y daughter atoms, that number Y, to accumulate from the parent atoms, and that is said to be the rock's age. So we can use this simple hourglass analogy. It's not perfect, but it helps people to understand. Effectively, the red sand grains at the top are the parent, the green sand grains at the bottom are the daughter. The falling is radioactive decay, And so as the red atoms fall, they turn into green atoms, parent turns into daughter. If we know the rate of falling, so for example, let's start with all the sand grains in the top bowl, and it takes 1 hour for all the red sand grains to fall to the bottom to become green sand grains, okay? So when we test the rock, we measure how many red and green atoms there are, and so we look at the top, we see how many red atoms are still in the hourglass. We look at how many green atoms are at the bottom. So, for example, if we see that half the sand grains are still at the top, the red one's about half the quantity, and at the bottom we've got half the quantity now are green atoms. How long has our clock been ticking? We know it clicks for an hour, and therefore half and half an hour. It's been ticking for 30 minutes. So we need to assume that the rate of radioactive decay or falling has remained constant at today's measured rate. And of course, by looking how many red and green atoms we've measured, we can calculate how long back all the red atoms were at the top. So we know how long the hourglass has been operating. And so that's how the method works. We back calculate to determine when all the atoms were red atoms. That's the rock's age. Very simple analogy, but there's 3 critical assumptions even with this hourglass clock. I mean, we assumed that all the sand grains were at the top to begin with. Well, we know that because we were there to put them up there at the beginning. So let's look at these 3 critical assumptions. They're so crucial for these radioactive dating methods, more critical than an hourglass clock. So assumption number 1 is the amounts of parent and daughter atoms at the beginning when the rock formed, that is, the initial conditions must be known. So for example, with our hourglass clock, we started the clock by making sure all the red atoms were at the top. So we were there at the beginning to make sure that that was the case. And our clock will measure accurately because we now know the green atoms have been derived over time from the red atoms by falling, by radioactive decay. And so we can do that back calculation. But that assumes that there's an observer. We have to assume, for example, in our rock, that there were no argon atoms, green daughter atoms from potassium decay, in the bottom glass bowl. So that at the beginning, there was no inheritance. And we're going to look at some examples in a moment to illustrate this so you understand it better. But in other words, we have to know the starting conditions, but how can we be sure about the starting conditions? We were there with the hourglass clock, but the geologists weren't there millions of years ago when the rocks were formed. So they don't know for sure what the starting conditions were. They just have to assume they know the starting conditions. Assumptions number 2 is that all the daughter atoms measured today have only been derived by in situ radioactive decay of the parent atoms. In other words, the system has been closed. All the green atoms could only have come from falling or radioactive decay of red atoms. So in other words, there's been no contamination. I mean, what if when you're outside of the room, your hourglass clock is sitting there on the kitchen bench. While you're out of the room, your mischievous 10-year-old comes in, lifts up the lid and puts more red sand grains at the top. You come in and you think the clock has been only ticking for 10 minutes when it's actually been ticking for half an hour because he's added extra sand grains at the top. He's contaminated the system. And so were the geologists there for millions of years to watch these rocks that there was no contamination? I mean, groundwater moving through rocks leaches out elements. And so we know contamination occurs today in the real world. So what about in the past? And then, of course, the obvious third assumption is the radioactive decay rate must have been constant at today's measured rate. We have to assume that we know the rate of falling. We measure it today as red atoms turn into green atoms. But this requires an observer. We've only measured the decay rates in the labs over the last 80 odd years. And so how do we know that the decay rates have been constant through millions of years when geologists weren't there millions of years ago to check those decay rates? So it's obvious that we've got these three crucial assumptions. Number one, no initial inheritance. Number two, no contamination. No other process has affected the parent-daughter relationship. And number three, no changed rates. The decay rates have been constants. Now, it should be obvious that none of these assumptions are provable. The past cannot be observed and measured. We only exist in the present. We're extrapolating back into the past, but we can't go back into the past to check. We also know that these three assumptions are not even reasonable. We know we get contamination today. We know that new volcanic rocks have inherited, as we're going to see in a moment, argon from the volcanic gases. We know that geological processes change. Even, you get a local catastrophe today when you have a hurricane or you have an earthquake. We know that the geological processes change their rate and intensity. So these assumptions are not even reasonable. And we also know that these three assumptions have been repeatedly falsified. And we're going to look at that in a moment. Daughter atoms are known to have been inherited when rocks form. And when they're not even detected, when we don't even detect the inheritance, doesn't mean there hasn't been inheritance. How do we know? Assumption number one, no inheritance has often been violated. And subsequent contamination is common. Again, even if it isn't detected, it doesn't mean that contamination isn't present, because it could be systematic. And I'm going to show you an example of that, of systematic contamination. So assumption number two, no contamination is often violated. And we're going to see that several lines of evidence have demonstrated conclusively that decay rates were grossly accelerated during a recent past catastrophic event. So assumption number three, no change rates, is violated by demonstrated past accelerated radioactive decay rates. Now, I want to add here an important caveat. The quality of the chemical analyses of these rocks is not disputed. They're repeatedly confirmed. I mean, I can send, first of all, they're well-constructed laboratories, ultra-clean labs. They spend millions of dollars constructing these laboratories. The equipment is amazing that they use to do these analyses. And I can get one rock sample and break it into 5 pieces and send those 5 pieces to 5 different laboratories, and I can guarantee that each laboratory will come in with essentially the same results. So I'm not disputing the chemical analyses, but that's a chemical analysis of red and green parent and daughter atoms. It's the interpretation of those analyses as millions of years ages based on these 3 unprovable, repeatedly falsified assumptions. That is what we're disputing here now with the examples I'm going to give you. And many of these examples come from the secular conventional literature. Many of them come, particularly in the early part of this presentation, come from textbooks that are used to teach geochronology, the science of dating rocks, in university courses. So it's not my words. You can go to the conventional literature and see these examples for yourselves. This one, of course, was done by Dr. Steve Austin, creationist geologist at Mount St. Helens. After the 1980 eruption, there was a new lava dome formed inside the crater, and geologists monitored various lava flows that flowed out of this new lava dome. And here's Dr. Steve Austin. He went up there to collect a sample from that new lava dome. And this is a 1986 lava flow. the volcanic rock is called dacite. It's a variety of volcanic rock. And he sent a sample of that for dating. In 1996, we knew it was 10 years old because we'd actually witnessed its formation in that new lava dome. And these are the results that were obtained. Potassium argon whole model ages, that is single sample ages. There's an equation to do the calculations. And you can see the whole rock gave one age. He separated various minerals, and a pyroxene concentrate gave an age, that's a mineral pyroxene, gave an age of 2.8 million years old, using potassium argon for a rock that we knew from observation was only 10 years old. The conclusion was that not all the argon that was measured had come from potassium decay. There was excess argon in the rock that had been inherited because there are gases in the volcanic eruption, and that includes argon, and some of that argon was trapped in the rock when it cooled and crystallized and cooled. But this is in the open literature. These results come from the conventional scientific literature. You can fly into the big island of Hawaii, land at Kona Airport, and right by the airport you've got the Hulalai basalt, the eruption 1800 and 1801. We know exactly when it erupted, but it gave potassium argon ages of 1.4 to 1.6 million years. There's Mount Etna there. We can see results there. A mineral plagioclase from the Mount Lassen in California, Sunset Crater in Arizona. We know when it erupted, and yet it gives a wrong age from potassium argon. In fact, they took lava flows that in Hawaii, and they did. You get big pillows, basalt pillows. When the lava flows down to the ocean, it congeals as big pillows, and they took samples from the rim of the pillow, and then inside the pillow, this bulbous mass of basalt, and you can see it got younger as you went further and further into the sample, and so in the pillow, and so. This is because argon gets trapped from the volcanic gases. And this is well known in the geological literature. And I might add here that one of the critics of Stephen Austin's work at Mount St. Helens was G. Brent Dalrymple, who accused Steve Austin of using the wrong method. And, you don't use potassium argon to date young volcanic rocks. But you can see one of the authors here in this list of references is Dalrymple. Some of these examples come from his work. These are known historical aged lava flows, and they give incredibly old ages due to excess argon. So even in the conventional literature, they were doing this work. So it's a case of the pot calling the kettle black if a critic who does the same work criticises a creation geologist for doing exactly the same as he's already doing. This is in the literature. 10 diamonds from the Democratic Republic of Congo yield a potassium argon isochron age of 6 billion years. Well, they knew that was wrong, because how could 6 billion year old diamonds, there be 6 billion years older diamonds when the Earth is only 4.5 billion years old? So obviously the argon was inherited. The diamond inherited extra argon, and later on, of course, they found out that it was trapped in fluid inclusions, tiny micro fluid inclusions. In Africa, 2 volcanic centers, that is 2 volcanic areas of volcanic eruptions, 100 miles apart in the African Rift Valley, that were known to have lavas less than 1 million years old, supposedly, yielded a rubidium-strontium age, isochron age, of 773 million years. And I'm pointing out this is an isochron age because many people say that the isochron method is the gold standard. Well, here we have known volcanic rocks that give a false rubidium strontium age. And then on 14 different ocean islands, recent basalt eruptions, we know how old they are, we've seen them, we've historically documented, on 14 different islands in the different oceans, yielded a rubidium strontium isochron age of 2 billion years for recent lava flows. Again, an isochron age. And the same here. These are results of lead-lead dating, which is the uranium-lead, the two different isotopes of uranium. This is supposed to be the gold standard, lead-lead isochrons. And here we see these are recent lava flows, basalt lava flows on ocean islands all around the world. You can see their names. This is in the open scientific literature. They all yield lead ages of between 1 and 2 billion years. And this has been known in the literature as the lead isotope paradox. It's been known for over 50 years. And the conclusion is that the lead is inherited from the upper mantle source of these basalt eruptions. So we know it's inherited lead. Here's another example. This is again from the open scientifically. We go to the Western Grand Canyon, and those who have been on a raft trip through the Grand Canyon with me will know about some of these rapids produced by these lava flows, eruptions from craters on the North Rim in the Western Grand Canyon flowed down the walls, and they dammed up, they blocked the Colorado River. And these are recent lava flows. They're younger than the Grand Canyon itself. And then in the Eastern Grand Canyon, at the very bottom of the sequence, in the Precambrian, the older rocks of the canyon, in the inner gorge, we have the Cardenas basalt lavas, and these are supposedly over 1 billion years old. Well, here's these lava flows. This is one of these volcanic cones. You can see the lava flows that flowed into the canyon. Just around the corner, you can see the Colorado River down the bottom there. Just downstream of this point is the fastest navigable rapid in North America, 20 seconds of sheer terror. And here's these lava flows in the Eastern Grand Canyon that are flowed out and are between other layers deep down in the Grand Canyon rock sequence. Well, here they are, the youngest basalt lava flows in the canyon, the oldest lava flows in the Grand Canyon. And they give essentially the same rubidium strontium isochron age. Notice that, an isochron age. Why would the youngest lava flows give you the same rubidium strontium isochron age as the oldest lava flows in the Grand Canyon? Well, it's because all these lavas came from the same mantle source underneath the Grand Canyon. So we know these cannot be real ages. They must represent the chemistry of the same source. They give the same rubidium strontium isochron age. The same source must have the same rubidium strontium chemistry. So that rubidium strontium chemistry has been inherited by the lava flows when they erupted. It's nothing to do with the age of the lava flows. It has everything to do with the chemistry of the original basalt. So, assumption number one, we've used some examples to show that it's violated by inheritance. And I point out here a very important point. If we know that this assumption is violated for recent lava flows and lava flows whose age we know from observation, then can we trust it for ancient lava flows? How do we know that the ancient lava flows also haven't had some of their content inherited? And that's a point that most conventional geochronologists do not recognize, but they should. It's logical. Now, assumption number two, let's dive into this, that no other process has affected the parent-daughter relationship. Let's look at some examples. We can go to Mount Narahoe in the Taupo volcanic zone of North Island of New Zealand. And many of you will know that volcano. It was Mount Doom in Lord of the Rings movies. And here's the volcano itself. You can go in there. You can see different lava flows and different amounts of vegetation. And they've been identified, mapped, they've been witnessed. This was the 1954 lava flow you can see there. The lava flows to the right and left. They've got more vegetation, so they're older, and so it goes on. And here's a map of some of these most recent lava flows. We know, in fact, the day, the month, and the year of many of these lava flows. So these were sampled, and we obtained potassium argon ages up to 3.5 million years for these lava flows that were only a few decades old. And of course, that was inherited argon that gave you those old ages. But these lava flows also gave a rubidium-strontium isochron age of 133 million years from 5 samples. And the daughter isotopes, strontium, neodymium, and lead, and this is in the conventional literature, indicate that there was crustal contamination, 5 to 10% crustal contamination. The lava flow is called an andesite, named after the Andes in South America, because it's a basalt magma that was contaminated by crustal rocks, and it changed the chemistry from basalt into a resulting volcanic rock that's different, called an andesite. And so we know that contamination has been a critical part of forming these lava flows at Mount Narahoe. Here's another example. This is from the literature. A granitic rock in South Africa yielded a lead, and samarium neodymium isochron age of 2.9 billion years, 2,915 million years. The minerals within the rock yielded a rubidium-strontium isochron age of only 2,023 million years. A huge difference, nearly 900 million year difference between the rock, the whole rock, and the minerals in the rock by a different method. And one of the minerals, albite, in the rock yielded rubidium-strontium ages of 5,852 million years at its outer edge, and inside the mineral, it gave an age of 3,060 million years. So all these different conflicting ages from the same rock indicates there's been contamination. Different methods give different ages. Notice that? We'll come back to that in a moment. Here's another example. Out in Colorado, they looked at a granite that intruded into Precambrian schists, Precambrian metamorphic rocks that were supposedly 1,375 million years old. The granite intruded as hot molten rock, and it crystallized and cooled and released heat, and it released water. The granite was dated at 54 million years old. And so what they found is that the ages in the host rock, in the Precambrian schist metamorphic rocks, got younger. They decreased closer to the granite. The granite had released heat and water, and the heat and the water had decreased the ages of the host metamorphic rocks. And here's the published results. That red line there is that white line there, the boundary between the granite and the metamorphic rock. So there's the red line there. To the left is the granite. To the right is the metamorphic rock, the schist. Notice the age out to 10,000 meters. That's 10 kilometers. You had to go out that far before you got the supposed true age. As you got closer and closer, the ages decreased remarkably as you got closer. So, 100 meters from the rock, from the granite, the potassium argon age and the biotite, coarse biotite, was essentially the same as the granite. So heat and fluids had affected the outcome and contaminated the metamorphic rock and changed the radioactive ages. Here's the uranium, lead, and lead ages. Again, the distance is less. It's only feet there on the bottom scale, but there's a significant decrease as you get closer and closer to the granite. Contamination from heat and fluids coming out of the granite and affecting the host schists, the host metamorphic rocks. Now, when granites cool, they often crystallize a mineral called zirconium silicate. It's a very important mineral because uranium substitutes into the lattice for zirconium, and it's used for uranium lead dating. It's only in small quantities in granites and other rocks, but it's a very strategic mineral. Now, it's supposed to be a component of the granite when it cools. But why do I put the word inherited in quote marks? Because that's the excuse used in the conventional literature to explain these results. A granite in the Himalayas, supposedly 21 million years old, dated by other methods, had zircon grains in it with uranium lead ages up to 753 million years. And so rather than say there was something wrong with the uranium lead age of the zircon, they say, oh, the zircon must have been inherited from the older rocks. But wait a minute, the zircon supposedly crystallized in the granite from the granite magma. There's another example there of a southeastern Australian granite from rubidium strontium, gave an age of 426 million years, but it had zircon uranium lead ages from in the granite of up to 3,500 million years. And then we had zircon grains in a New Zealand granite, supposedly 370 million years old, dated by other methods, giving zircon grains within it ages up to 1,638 million years. And that's their documented cases in the open literature. Why would the zircon grains that supposedly crystallized from the granites give such older ages from the granites themselves? Something is wrong with these dating methods. Here's an interesting example. A Himalayan granite, supposedly 20 million years old by other dating methods, has zircon grains with uranium lead ages up to 1,483 million years. But another mineral called monazite is also in that granite, and it gave uranium lead ages of minus 97 million years. In other words, minus 97 million years means the monazite grains haven't yet even formed. Something's obviously wrong. So you can see this is in the open scientific literature. This is not my work. This is done by conventional secular geochronologists. Contamination in these granites, contamination in these zircon grains. Here's another example. Now, argon dating is supposed to be one of the benchmarks. They used argon dating to date the Vesuvius eruption at Pompeii. Now, of course, they knew the target age, and of course, the argon got it right. But here's an example where argon didn't work. Okay, 2 biotite grains, and that black line is the boundary between those 2 grains. Those stars are data points where they zap the grain with an electron beam or a laser beam at a very narrow, only about the width of a human hair. That's how precise they could be in focusing on that size of a point to give an argon age for these biotite grains. And what did they find? That blue line is the edge between those 2 grains. Look at the age. The ages decreased as you went further and further into that biotite grain on the right. Why did it give such an old age its boundary? because argon had leaked into and contaminated the edges of these grains. So argon is a gas, so it's mobile, it can contaminate. Here's another interesting example. Again, this is published in the open scientific literature. They took a badallite grain, which is zirconium oxide. It's found in certain rocks, and it's nice, took a nice crystal. They set it up on a machine where they could focus a beam on it, an ion beam, ION, beam onto it, and they could do uranium lead dating of a spot on a crystal face. And they rotated that crystal, and you can see in successive pictures there, they rotated that crystal to zap the beam on different points on different crystal faces, so that the beam was at a different angle to the face. See that? The first on the left, it's 40. It's at perpendicular. You go to the right, it's at about 45 degrees. And so you can see there's different angles as the grains were rotated. What did the results show? The uranium lead dates varied by up to 400 million years depending on the angle of the beam on these crystals. Wow, just the angle of the beam on the crystal face gave a different age. So, assumption number 2, all these examples, most of these examples coming from the open scientific literature, were violated. Number 2, violated by contamination. We've demonstrated that contamination has occurred. And again, if we know where there is contamination, does that prove that where we get results that we want, that there's been no contamination? No. How do we know? Just because the results is what we want by other measures doesn't mean that there hasn't been contamination. How can we trust all the other dates? Now, it's insisted that assumption number 3, constant decay rates, is universally true. Why? Because the resultant millions of years ages are needed for evolution to be possible. And see, this is the crux of the matter. When they know the methods don't work, they disregard those results. Where the methods seemingly work, they accept those results because they prove what they want. That is, that the Earth is millions of years old, that there's been time for evolution to occur. In the history of geology, it was the millions of years that was established before, by other methods, before Charles Darwin propounded evolution. Evolution, you don't see it happening today, but given enough time, evolution occurred. So that's the argument. But why should radioactive decay rates have always been constant at today's measured rates? We know that other geological processes vary at their rate, so why not radioactive decay rates? Now, again, the 4 major methods that we're going to look at: potassium to argon, rubidium to strontium, the 2 uranium isotopes, parent isotopes to the 2 daughter lead isotopes, samarium to neodymium. Again, those notations are the atomic weights of the radioisotopes, the parent and daughter isotopes. Now, geologists only use 1 or 2 of these methods on the same rock samples because they assume that all methods would ideally use the same age for the same rocks, which in theory and practice they should. You know, we had those hourglass clocks. Let's have a uranium lead clock. Let's have a rubidium strontium clock. The red sand grains are different sizes because the uranium atoms are bigger than the rubidium atoms, but they should all fall, and they have different rates of falling because of their sizes, but they should all fall, and we can measure the rate of falling. And so if we start with all the red sand grains at the tops, all the different clocks, they should all fall, and we should be able to measure the green atoms now, and we should all get the same age by all the different clocks. Well, what would we expect to find if we used all 4 methods on the same rock units? And let's use the superior isochron technique. Model ages are based on 1 sample, Isochron ages are usually 5 or more samples from a rock unit, or 5 minerals from the same rock from a single sample. And if we use this superior isochron method for all 4 methods, we should expect very good agreement. This is the gold standard, so to speak. So, and I say we because this was research that I was involved in. We went into the Grand Canyon with an appropriate research and sampling permit. We took samples from top to bottom of this diabase sill. This is where a basalt magma is not erupted at the surface. It's squeezed like toothpaste between rock layers. And this is deep in the Grand Canyon. We're looking right down there. It's intruded into the Bass limestone at the bottom of the Grand Canyon sequence. So what results did we obtain on this rock? Which is the correct age? The potassium argon at 841.5 million years, rubidium strontium at 1060 million years, the lead, that is the uranium lead versus the uranium lead, at 1250 million years, or the samarium neodymium clock at 1379 million years. Now, each of these are significantly different from one another. Which is the correct age? What about E? None of the above. How will we know which is the correct age if we didn't have an observer back then to know when the diabase sill crystallized and cooled? And by the way, notice that the potassium argon and rubidium strontium are the youngest ages. I want you to see that there's an order in the sizes of these ages. There's a systematic pattern that we're going to see. And potassium and rubidium are beta decayers, whereas uranium and samarium are alpha decayers. It's the type of radioactive decay. They're different modes of radioactive decay when the nucleus spits out a particle. Okay, let's look at these Cardenas basalts. We met them earlier in the eastern Grand Canyon. Here they are from one of the easternmost overlooks. You can go to Desert View Tower, easternmost overlook at the south rim of the Grand Canyon. You see these Cardenas basalt lava flows. They're down deep in the canyon. Here they are up close and personal. These were sampled. Which is the correct age? Potassium argon isochron age of 516 million years. Well, we know that's wrong. Why? Well, conventionally, we know it's wrong because the rocks over on top of it are younger, almost the same age, and that doesn't work. Rubidium strontium, 1,111 million years. Samarium neodymium, 1,588 million years. Notice that rubidium strontium age is double the potassium argon. The samarium neodymium is triple the potassium argon. And these are isochron ages, by the way. And which is the correct age? Could it be none of the above? Notice, by the way, that the potassium argon is the youngest again. And by the way, I put up here the isochron that was plotted, and notice that the isochron doesn't go through zero. There was excess argon in this lava flow. The ancient lava flow also had excess argon, like the historic lava flow. Again, evidence that the ancient lava flows also had excess inheritance, and therefore the results cannot be trusted. Okay, and then the third rock unit, deep in the Grand Canyon, there are lava flows that were metamorphosed into a rock called an amphibolite. And this is a crystalline basement in the inner granite gorge of the Grand Canyon. And we're right down at the very bottom of the Grand Canyon here. And so what results do we get? A rubidium strontium age of 1,240 million years, a lead age of 1,883 million years, and a samarium neodymium age of 1,655 million years. Which is the correct age? Notice the rubidium strontium, the beta decayer, is the youngest again. Systematic. And the Ell's Chasm granodiorite, one of the supposedly the oldest rock in the Grand Canyon. And what results did we get on that? Here it is, right down there in the crystalline basement. Rubidium strontium age of 1,500 million years. Lead over 1,900 million years. Samarium over 1,600 million years, which is the correct age. Again, notice there's a systematic pattern. And so if there's a systematic pattern, it means there's a systematic process going on that's causing these discrepant ages, these discordant. And these are isochron ages. They don't concord with one another. They don't agree with one another. So these multiple radioisotope ages on these 4 rock units give different ages. They always disagree. But each of these rock units represents a unique or once only geological event. For example, the formation of the sill, when the molten rock was squeezed between the layers. That was a one-off geological event. The volcanic eruptions that caused the Cardenas basalts, the metamorphism of the lavas that produced the amphibolites, and the crystallization of the granite. If these radioisotope clocks were accurate, always ticking at the same rates as we measured today, each clock should have given the same age for example, these Cardenas basalt lava flows. So what can we conclude? The different ages from each radioactive clock means that the clocks must have been ticking at different faster rates than what we measure today. So when the Cardenas basalt was crystallized, in the real time between when it crystallized until today, so there is a single real-time period from the formation of the basalt till today. In that real-time period, the potassium argon clock ticks through 516 million years, but at the same time, the rubidium strontium clock ticks through 1111 million years, so it was going faster than the potassium argon clock. And the samarium clock was ticking even faster and clicked through 1,588 million years. The potassium is the smallest atom, the lightest atomic weight. Rubidium strontium is a heavier atomic weight. Samarium is an even heavier atomic weight. So the larger the parent atom, larger the atomic weight of the parent atom, the faster the clock ticked. So this means there was a systematic pattern. There was faster rates in the past. That means there was systematic accelerated nuclear decay. And it was according to the different atomic weights. And we plotted all this up, and we could demonstrate that the atomic weight and also the mode of decay, beta decay versus alpha decay, affected the rates at which the clocks were accelerated in the past. So, assumption number 3, constant decay rates, is violated by evidence of accelerated decay rates. Different isochron ages by different methods on the same rock units can be explained by accelerated decay rates in the past. So what has the scientific community done with these problems? They've ignored them. They've ignored these assumptions. They've convinced themselves that the isochron technique supposedly eliminates the need to know the initial conditions, and it supposedly indicates contamination. How does it do that? When the samples plot on the isochron line, they assume that the isochron is a true age. Any sample results that don't plot on the isochron are discarded. That's contamination. And I'm going to show you some examples now in a minute of where that doesn't work. So we keep going here. The reason they accept these methods, as I said before, is they seem to work because they give results that are required ages of millions and billions of years to help the evolution. And of course, the results, the rock layers are in the right order, the results. So layers at the bottom of the Grand Canyon give you an older radioisotope age than layers at the top of the Grand Canyon. But that's works the same as with accelerated nuclear decay. For example, if you had a lava flow in the first month of the biblical flood, and then another lava flow higher up in the sequence in the last month of the biblical flood, then the lava flow at the bottom of the sequence would have ticked through 11 months of accelerated radioactive decay, and so it obviously would give you an older radioactive decay result than a lava flow from the last month of the flood. It only ticked through 1 month at the end of the flood. So you can see the right order works whether you accelerate the decay rate or not. And so this is important to remember. Isochrons can also indicate inheritance, as we've already seen, and we're going to see, and not all isochrons provide real isochron ages. And this is documented in the literature, and I'm going to come back to this in a moment. So isochrons are straight lines. They're based on chemical analyses of 4 or more samples or minerals of the same rock unit. They claim to represent the age of the rock unit, but do all such straight lines always represent ages? Let me give you an example. And this was work that I was involved in, research that I was involved in with Australia's premier scientific government agency called the Commonwealth Scientific, Industrial and Research Organisation, the CSIRO. And I was involved. In fact, I did my PhD dissertation on the Koongarra uranium deposit in northern Australia. You can see there on the map. And we were looking at soils as an exploration method. We were looking at the lead isotopes in soils. Spectacular countryside. If you ever saw the movie Crocodile Dundee, it was set up in this country. In fact, the second Crocodile Dundee movie, they used the airstrip that was used for the exploration camp of the Koongarra uranium deposit that I was involved in. And here's an aerial view. You can see the drilling grid where they did the drilling to confirm the uranium in that deposit. Here's a photograph of the one of the drill cores with the uranium, the uraninite, uranium oxide, and the alteration minerals that I studied in my PhD dissertation. And as I said, we were collecting soil samples from above the uranium deposit, which has obviously had lots of lead in it. And then we went away and collected soil samples from up to 20 miles away over the other side of a mountain and looked at the lead isotopes in that, because we wanted to show that the lead isotopes were a fingerprint of where there was a uranium deposit underneath. And so that's obviously a way you can explore for new uranium deposits. You go to the known and you go out to the unknown. What did we find? We found that these soil samples, even up from 20 miles away, fitted an apparent isochron age. And the fit was 99.986%. You can see that. It was almost a perfect fit. The soil samples from over the uranium deposit and the soil samples from up to 20 miles away fitted onto that isochron line. It was a mixing line. It wasn't a true isochron age. The soils weren't that old. And so we know that isochrons can be mixing lines. And in the literature, there are what are known as documented called mantle mixing lines. And I gave you an example of that before. The rubidium-strontium isochron ages up to 2 billion years from different ocean islands, those were called mantle mixing lines. They weren't true isochrons. And so not all isochrons are real isochrons. Here's a documentation of the strontium and neodymium isotopes in granites in southeastern Australia of different source materials. The granites were derived from We call them I-type and S-type granites. Igneous rocks were melted to form the granite, or sedimentary rocks were melted to form the granites. And notice the strontium, rubidium, strontium, the daughter strontium, the samarium, the neodymium isotopes fitted on a mixing curve. And so we know that the daughters show mixing lines, mixing curves. And so, again, not all isochrons are real ages. They can be mixing lines even when we think they give valid real isochron ages. So isochrons, even with an excellent fit of the data, are known instead to be mixing lines. In a paper in Chemical Geology, the authors wrote that even when you get an excellent fit to the data, you can still have a mixing line. It's there, the quotes in the literature, it's not me. And so for example, the mixing line for the soils is neither an age for the soils or for the rock units the soils were derived from. So all such straight lines do not always represent real ages. Now, is there other evidence of past radioactive decay rates being accelerated? Yes. It's not just based on using different isochron methods on the same rock units. There are 3 other lines of evidence that we need to delve into quickly that confirm that past radioactive decay rates were accelerated. And these are helium diffusion, polonium radiohalos, and radiocarbon. So let's quickly look at these 3. Helium diffusion. Helium is a byproduct of uranium decay. When uranium decays to lead, it goes through 8 steps, 8 alpha particle decay steps. The alpha particle is 2 neutrons and 2 protons. It goes out into the zircon where it picks up stray electrons. And so it gets 2 electrons to balance the 2 protons, and that's a helium atom. So helium is actually a byproduct. Every uranium atom decays to produce 8 helium atoms. Deep drilling, they drilled a drill hole near Los Alamos, New Mexico. It's called Fenton Hill. And they drilled this deep drill hole into this granite to where they knew the rock was warmer to explore for using geothermal energy. And that granite, in that granite were different zircon grains, and they recovered zircon grains from different depths in that granite, down in that drill hole. And of course, they knew the temperature. They could measure the temperature in the drill hole from where they collected the samples, from where they got the zircon grains. Okay, and so they also knew the age of these zircon grains, and the uranium lead age, it's in the literature, was published. The uranium lead age for these zircon grains was 1.5 billion years, 1,500 million years. So here's the different depths down on the left there. The helium was retained in these zircon grains that was measured. You can see the temperatures. At 750 meters down, the rock was 95 degrees warm. You go down to 960 meters, it was 105 degrees Celsius. That's above the boiling point of water. So it was quite warm. No wonder they were looking for geothermal energy potential. Notice how much helium was retained. At 750 meters, 80% of the helium that would have been produced by 1.5 billion years of decay was retained. But as you went down the drill hole, the hotter the rock, the less helium was retained. Why? Because helium leaks out of the zircon grains. It's lightweight. The hotter the crystals, the faster the helium leaks out. Helium is a lightweight atom. No, it's only atomic weight 2. It's fast moving. The warmer the atom, the more energy it has to wriggle its way out. and it can slip easily between the zirconium, the zirconium crystal in the zirconium crystal lattice, which is made up of zirconium, silicon, and oxygen atoms. So, taking those results that were published in the literature, the helium leakage rate determined by how much percentage that was retained, okay, 1.5 billion years worth, 80% retained at 750 million years. What's the leakage rate? Go down deeper, hotter, a higher leakage rate. So we plotted the leakage rate versus the temperature on this graph, okay? And before the leakage rates from these zircon grains were actually measured in the laboratory, we made predictions. The leakage rate equals the helium lost 80% over the time, okay? So for 1.5 billion years of decay, how long did it take for 20% to leak out? That was the leakage rate. But if instead it was only 6,000 years, the biblical creation model, thereabouts, 6,000 years, then the decay rate, the leakage rate would have been faster, because 20% would have been lost in 6,000 years rather than in 1.5 billion years. So you get where I'm going here? So when we plotted that, the leakage rate on the left, diffusion rate, versus the temperature, for the two different models, the 6 samples, 2, 4, 6 samples, gave two curves that were a factor of 100,000 different. 6 orders of magnitude different. 5 orders of magnitude different. And we predicted these, published these predictions before we sent our own samples away for further testing to actually measure the decay rate. The diffusion rate. Okay, so we predicted if the diffusion rate was very fast, it would fit the 6,000 years creation model. If it was very slow, it would fit the 1.5 billion year model. Okay? The leakage rates were measured in a world-class laboratory by a secular geologist who didn't realise where the samples had come from and who had sent the samples. And look at the data. The black dots, the top right there, at the lower temperatures, they overlapped with the 6,000 year model. They didn't fit the 1.5 billion year prediction. Wow. Talk about an experimental confirmation. Furthermore, if we look at these leakage rates and the amount of retention of helium, we can calculate the various diffusion rates for each of those samples. And the average is almost 6,000 years, a little less. Wow. How can we reconcile these two clocks? Remember, helium diffusion is a physical process that follows a known physical law, the diffusion law. Okay? So here we have two clocks. The helium diffusion gives an age of only 6,000 years, and that helium is derived from 1.5 supposed billion years of nuclear decay to form lead. And they disagree by millions. How can we reconcile these clocks? We can reconcile them if 1.5 billion years worth of nuclear decay, as measured at present decay rates, in fact occurred in only 6,000 years. In other words, that uranium decay was accelerated grossly at some past catastrophic event. So that's further confirmation of accelerated nuclear decay in the past. Well, also in granites and schists. Now I add here schists, metamorphic rocks. The reason why I keep on emphasizing that this is both in granites and schists, we find biotite grains, which is a black flaky mineral. It's called mica, and the black variety is called biotite. The white variety is called muscovite. The reason I'm mentioning schist as well as granite is because some of our critics try to tell us that what I'm going to talk about, radiohalos, form in granites by a different process. But wait a minute, that same critic does not recognize that these same radiohalos form in schists, in metamorphic rocks, which is a totally different rock. And so he's blind. He's focused on granite, and nobody else agrees with him, by the way, on his argument for the formation of granites. Mainstream scientists do not accept his idea for the formation of those granites. And these radiohalos are also found in schists. So I mentioned that right up front. So embedded in the biotite grains, okay, not only are zircon grains found in the granite overall, but sometimes tiny zircon crystals are embedded within these black biotite grains. They got trapped between the layers called the sheets, the mica sheets, the crystal sheets of biotite. You can actually peel a biotite flake apart like the pages of a book. The zircon crystals have been trapped between the pages of the book. And so the zircon grains within the biotites contain radioactive uranium atoms. They decay and they eject alpha particles. Okay, we're familiar with that process. And each uranium atom goes through 8 decay steps. So there's 8 different alpha particles. At each step, it's a different daughter atom that spits out the alpha particles. Because it takes 8 steps to get down to a stable lead atom. But in the process, there are different daughter atoms that become the parent for the next step of the alpha decay chain. Okay? And we know what those elements are. So when the zircon crystals are large, for example, 60 microns long, that is about 6 times the thickness of your hair, the alpha particles stay within the zircon crystals and they become helium atoms within the zircon crystals. However, when the zircon crystals are only tiny, only 1 micron in length, the alpha particles escape from the zircon crystal and they're ejected out into the surrounding biotite flakes. Okay? So here on the diagram on the right, you can see the little grey dot. That's the zircon crystal. Each of those arrows in 3 dimensions is spitting out in a spherical halo these alpha particles. Okay? And these alpha particles are like little bullets. They damage the crystal structure of the biotite around them, discolorating it. And those discolorated areas are in a sphere or a halo. And because it's produced by radioactivity, it's called a radioactive halo, or radiohalo for short. Okay? And you'll see on the right, there's a darker area and there's a lighter area. And you can see the little zircon crystal at the center of the flake. And I want you to notice something else. The biotite flake that hosts us is both brown and green. That's because the biotite flake has been altered to green as a result of hot water. That's an indication. The biotite flake, when it's pristine, is usually brown. When it's altered by hydrothermal fluids, hot waters, it turns green. Okay. So at each step of the alpha particle decay chain, okay, uranium decays with 1 alpha particle step, it goes to uranium-234, decays to 238, to 230 thorium, decays to 226 radium, decays to 222 radon, decays to 218 polonium, 214 polonium down to 2110. At each of these steps, the parent atom shoots out an alpha particle of a different energy, okay? And different energies mean the different bullets travel different distances. Okay, it's like having a a handgun and a rifle. A handgun won't shoot the bullet as far as a rifle. The rifle will shoot it at a greater distance. And it's like that. Think about firing a gun into a drywall. It'll damage the drywall. So it's like that. The alpha particle bullet will damage the crystal around it. Okay? It's been determined that a fully formed dark uranium radiohalo, which has 8 rings, you can see it there, fully formed, it requires between 500 million and 1 billion alpha particles. Okay, it takes that many to leave enough damage to make the darken the biotite sufficiently so that we can see it. And that amount of alpha particles is equivalent to at least 100 million years worth of radioactive decay at today's measured decay rate. Okay, so every radio halo that you can see under the microscope, because these are examined under the microscope in the biotite flakes, every radio halo takes at least 100 million years worth of radioactive decay to produce it. Now, granites and schists around the world, and I've looked at samples, and others have too, from around the world. Some of this is in the open scientific literature. It's been known for over a decade about these radiohalos, and from schists as well as granites. And that means all these granites and schists contain observable physical evidence of abundant nuclear decay of at least 100 million years worth of decay at today's measured rate. But in many granites and schists, okay, we've now looked at radiohalos in general. Uranium radiohalos, a fully formed uranium radiohalo. Now let's look at what are known as polonium radiohalos, because in many granites and schists, not just granites but also schists, the biotite flakes in them have radiohalos consisting of only one small ring, and we find them alongside the uranium radiohalos, as in this example here. And the diameter of that one small ring matches the energy of polonium-210, the last step. So that means this one ring small radiohalo was parented only by polonium-210. In some granites, we have biotites and with flakes, granites and schists, with radiohalos consisting of only 2 rings. And they're alongside dark uranium radiohalos that are fully formed. Now, this dark uranium radiohalo, by the way, has had so much decay that the inner rings are lost. It's very, very dark. So that's well over 100 million years worth. And the arrowed radiohalo there has only 2 rings. And those 2 rings fit with the energies of the polonium-214 and the polonium-210 parent atoms. And so that means this 2-ring radiohalos was parented, the outer ring by 214 decay, polonium-214 decay, the inner ring by polonium-210 decay. So because it was parented by initially by 214, we call these polonium-214 radiohalos. And then occasionally, in these same granites and schists, there are biotites that with radiohalos that consist of 3 rings. And those 3 rings match polonium-218, polonium-214, polonium-210. And because the first ring was parented by 218, we call these 3-ring radiohalos polonium-218 radiohalos. And notice they are independent of the uranium radiohalos, which means the polonium that parented these radiohalos was independent of the uranium. And that's significant. Okay? These radiohalos were produced by the last 3 steps in the uranium decay chain. And as I said, they're found with uranium radiohalos in many granites and schists around the world. I've just recently published a paper on the metamorphic rocks in the Grand Canyon that contain these radiohalos, as well as granites in the Grand Canyon that contain these radiohalos. Now, these polonium radiohalos, by the way, there was a famous 1989 court case in Arkansas, and in that Arkansas trial, US court case, these radiohalos on the witness stand were called a very tiny mystery. Why are they regarded as a tiny mystery? It's because these polonium radiohalos are so unstable, they only have fleeting existences. Polonium-218 has a half-life, a decay rate of 3.1 minutes. Polonium-214, 164 microseconds. If you blink, it's gone. Polonium-210, 210, 138 days. So that means with such extremely rapid half-lives, these polonium radiohalos had to form extremely rapidly. But here's the problem. How did you get the polonium concentrated? Robert Gentry, who pioneered some of this work in the 1960s, claimed there was no natural processes that could form these polonium radiohalos. He claimed there had to be a concentration of 50% polonium radiohalo in the radio center. That is in a central nucleated part. We call it a radio center, a nucleated center that would then spit out the alpha particles. The zircon grain in the uranium is called the zircon radio center. Well, there had to be a polonium-bearing radio center, and you need at least 50% concentration of polonium, he said, to produce these radiohalos. And so for a polonium-214 radiohalo, you had to have 50% of the necessary 214 polonium concentration transported to form that radio center within a millisecond or two, within a blink of the eye. And that's why he regarded these as indicating the rocks were created. He thought, well, it took the blink of an eye, creation took the blink of an eye, and the radiohalos polonium formed in the blink of an eye. But would God create polonium radiohalos and then allow uranium halos to subsequently form alongside them over millions of years in the same biotite flakes? These coexistent polonium uranium radiohalos are often found in granites and schists. However, that could have formed during the flood. So, for example, others before me and myself looked at granites that had intruded into and crystallized within fossil-bearing sedimentary rock layers. And from a biblical perspective, those fossil-bearing sedimentary layers formed during the flood. And that means the granites formed during the flood, the radiohalos formed during the flood, including the polonium radiohalos. So the granites weren't created. There had to be some other process that could form these polonium radiohalos. It required a new model. Now, think about it. Since these polonium element is a rare element, polonium is a very rare element, how could it form these radiohalos? How could it be concentrated separate from uranium in a separate place from uranium? But here, the radiohalos are in the same biotite flakes. And the only nearby source of uranium in the biotite flakes to where you find the polonium radiohalos is actually the zircon grains. The zircon grains have uranium that are generating uranium radiohalos in the same biotite flakes. So that means the polonium had to come from the uranium that was generating uranium radiohalos at the same time as the polonium was being separated and nucleating to form alongside polonium radiohalos at the same time in the same biotite flakes. So there had to be a way of taking the polonium from the zircon crystals as the uranium decayed polonium to separate locations within the same biotite flakes and adjacent biotite flakes, I might add, to form the polonium radiohalos. And this had to be done. The uranium decay had to deliver enough polonium rapidly to generate 500 to 1 billion alpha particles for each dark polonium radiohalo to form before all the polonium had decayed. So in other words, the uranium had to be speeded up, its decay had to be speeded up, accelerated to produce enough polonium very quickly for it to be transported elsewhere to form polonium radiohalo before it could decay away. So this was immediately evidence for accelerated nuclear decay of uranium. The polonium radiohalos wouldn't exist unless you had accelerated decay of uranium. Now, by the way, we also found in this research that the slower the decay rate, the faster the acceleration decay rate. So, for example, potassium had a faster decay rate than uranium. Potassium-argon ages were younger than uranium-lead ages. Therefore, uranium had been accelerated more than potassium. And so when polonium has a very fleeting decay rate, means that with accelerated nuclear decay, the polonium decay rate would not have been speeded up all. The same as with radiocarbon, has a very rapid decay rate, so it would not have been affected by accelerated nuclear decay. That's an important point to make before we go on here. So that means at least 100 million years worth of uranium decay has to occur within days to form the polonium radiohalos. So how do we get this concurrent uranium and polonium radiohalos? We need to remember that it's been observed and experimentally determined that radiohalos can only form below 150 degrees C, which geologically is cool. Molten granite forms at 650 degrees C. A basalt erupts at over 1,000 degrees C. Okay, so 150 degrees is cool. But above the 150 degrees, the alpha particles are annealed, they are destroyed. It was found that as they went down that drill hole at Los Alamos, the same drill hole from which the zircons were sampled for their helium diffusion, the radiohalos in the biotites in that granite were also looked at. We knew the temperature going down the drill hole. At 150 degrees, the radiohalos disappeared because they were wiped out. So that means radiohalos can only form below 150 degrees. The uranium radiohalo forms around the tiny zircon crystal. Uranium decays in the zircon to supply the radium and polonium, and we have infiltrating hydrothermal fluids that are under pressure. As the granite cools, the granite releases water, hot water. We know this. As magmas cool, they release waters. We see that at Yellowstone. That's why we've got the geysers. And that water is under pressure, which helps to force it into the rocks, helps to force the hydrothermal fluids between the sheets of the biotite flakes. You know, critics say, but how could the hydrothermal fluids go through the crystal in the crystal lattice? It's because of the pressure at those temperatures. So the hydrothermal fluids travel between the biotite sheets, along the cleavage, which is the break between the pages of the book. The hydrothermal fluids pick up radon and polonium from the uranium that's decaying in the zircon crystal, carried across to adjacent site. Now, because it doesn't decay in transport, it doesn't usually leave any sign, but in some cases, we see staining along fractures. So we know that there's been radiation stains. We know the fluids have transported along the fractures, and radon and polonium have decayed as the fluid has been transported along the fractures. But the polonium concentrates in radio centers, such as where there's a sulfur atom or a chlorine atom, because we know that polonium is like lead. It loves chlorine, it loves sulfur. And as the polonium decays after uniting with a sulfur atom or a chlorine atom, it decays, then the chlorine atom or the sulfur atom is ready to receive another polonium atom from the fluids. And so what happens, progressively the fluids transport the polonium. The radio center sucks up the polonium, decays, sucks up more polonium, decays as more hydrothermal fluids bring more polonium atoms. And so as they're transported, they decay, then more polonium forms on the radio center and eventually builds up progressively as the hydrothermals transport the. So you don't have to have 50% concentration all at once. All you need is accelerated nuclear decay of uranium at the source and rapid transport hydrothermal fluids under pressure going along fractures between the cleavage planes, progressively transporting the polonium where it's nucleated in geochemically conducive radio centers where it decays, more polonium is added from more hydrothermal fluid, and it builds up and progressively decays, produce these polonium radiohalos. So what evidence do we have that rapid hydrothermal fluid transport of polonium has produced these adjacent polonium radiohalos? Well, first of all, the short half-lives of polonium-218 and 214. 3.1 minutes and 164 microseconds. Unless it's rapid, you don't form those polonium radiohalos. The distances of transport are short. They're less than a millimeter within the same biotite flakes usually. Furthermore, we now have empty bubbles at the centers of nearly all the polonium radiohalos. That means they were fluid bubbles, fluids that contain the polonium radiohalos that is no longer there. And the last evidence is my research has shown the greater numbers of polonium radiohalos are found where there were greater volumes of hydrothermal fluids involved. And you can go on the webs, you can go to the literature and you can see my papers on radiohalos where I tested this, and I found that where there were greater quantities of hydrothermal fluids, you always found greater numbers of polonium radiohalos. So there are these supporting evidences that this was the case. So what conclusions do we reach? Dark uranium radiohalos in many granites and schist metamorphic rocks around the world are observable physical evidence that abundant nuclear decay has occurred at least 100 million years worth at today's measured rates. And coexisting polonium radiohalos in many granites and schists around the world had to form at the same time, and so observable physical evidence that this abundant nuclear decay had to occur at an accelerated rate. Such an accelerated decay rate would be expected to generate enormous volumes of heat, as some argue, and that would have potentially caused a major heat problem. And you'll get critics that will say, oh, but it would have melted the rocks. But wait a minute. We know from observed and experimentally evidence determined that radiohalos can only form below 150 degrees C. Otherwise, the tracks disappear. So there cannot have been a heat problem. Otherwise, there would have been no radiohalos to have survived. So the very existence of the radiohalos indicates that there was no heat problem when these radiohalos formed as a consequence of this accelerated nuclear decay. It means that there must have been some other process that dissipated all that heat, supposed heat. Finally, let's quickly look at radiocarbon. What is radiocarbon? Carbon has three isotopes, 12, 13, and 14. Normal carbon is carbon 12, makes up nearly all carbon. Radiocarbon is carbon 14. It's unstable. It has too many neutrons in its nucleus, and it decays. And here how it works. Unlike the other radioisotopes that are in rocks, radiocarbon forms differently. Up in the atmosphere, we've got lots of nitrogen-14. Cosmic ray bombardment from outer space produces high-energy neutrons that collide with nitrogen-14. 70% of the atmosphere is nitrogen, so there's lots up there. It captures the neutrons, and they become carbon-14. The carbon-14 combines with oxygen to form carbon dioxide. Down in the lower atmosphere, plants absorb that radiocarbon in the carbon-14 that they use in photosynthesis. That goes into the plants. The carbon in the plants 14 is added to what the animals eat, and so the animals get carbon-14, and then the animal dies. The carbon-14 in the animal's bones decreases after the animal dies. The older the burial of the animal, the less carbon-14 is in the bones. Then we sample the animal's bones. We measure the amount of carbon-14 in the animal's bones now. We compare it to the carbon-14 in animals alive today, and we know how long the greater amount in animals today, the lesser amount in animals that are buried, whose bones are buried. We know how long it takes for carbon-14 to decay, so we can calculate how long ago the animal died, because it's only got so much carbon-14 left in its buried bones. So that becomes the carbon-14 or radiocarbon age of those bones. It's that simple. It's not hard to understand. So radiocarbon decays at a steady rate back to nitrogen-14. That can be measured. It's called the decay rate. It's measured in units of half-lives, the time it takes for half of the original atoms to decay. The half-life is 5,730 years. So if you start with a pound of carbon-14 atoms, after 5,730 years, you only have half a pound left. But that means with aging, the carbon-14 content rapidly declines. So you lose half in one half-life, you lose half of that half in two half-lives, so very quickly you have less and less amounts. So virtually after 10 half-lives, you have none left. And so if every atom making up the Earth was carbon-14, radiocarbon, within 1 million years you can calculate it would all have decayed away. So that means if fossils are truly millions of years old, then fossils should contain no radiocarbon. And that they referred to, therefore, as being carbon-14 dead. No radiocarbon, dead, because they're so over 1 million years old, and not should all of that decay away. Well, since the 1980s, they developed a spectrometer, a mass spectrometer called an accelerated mass spectrometer, AMS shortly, for short, that can more accurately do radiocarbon dating, and now it's routinely used. That can virtually count 1 in a trillion carbon atoms as radiocarbon. That's how accurate it is. And we can work out the instrument's theoretical detection limit. It can go down to counting 0.001% modern carbon. Modern carbon has a certain radiocarbon content, and if you look at ancient materials, the smaller amounts is called percent. It's measured in terms of percent modern carbon, and so 0.001% modern carbon is equivalent to an conventional age of 95,000 years. That's the theoretical detection limit of these instruments. The practical detection limit is about 70,000 years from what they've worked out. Now, even secularists were concerned about problems with radiocarbon dates going further back in time because they were in such minute quantities of radiocarbon were being measured. They thought that they might be swamped by any contamination of samples in situ, contamination due from handling in the field or handling in the lab or from the lab equipment, even from the measuring instrument itself. So they wanted to check this lab equipment. They also made sure that they did very harsh pre-treatments of samples. These pre-treatments involved repeated washing with strong hot acids and strong hot alkalis, repeated washings. So they could think they worked out that this pre-treatment, they got rid of any contamination from handling or from in the field or from lab equipment. And these are very well-built laboratories that are built to avoid contamination. And so they put samples like that have been treated so harshly into their labs. They took samples that were they treated samples that were supposedly millions of years that should contain no radiocarbon and should be carbon-14 dead. So, for example, samples of coal or oil or fossils or limestone, and they pre-treated them like that. They put them in the instruments, and what did they find? Every sample contained detectable carbon-14. Coal, oil, natural gas, limestone, marble, various fossils that were supposedly millions of years old, supposedly radiocarbon dead. Every sample contained detectable radiocarbon. They even put samples in, they even put empty sample holders in the instruments, and they got a zero result. So they concluded that it couldn't be the instrument. The carbon-14 had to be in the coal, fossil, and other samples, and to be intrinsic to them. Now, the logical conclusion would be that the samples were not millions of years old. But you'll go to the literature and skeptics will keep on claiming that this is all due to contamination. But wait a minute. The samples were pre-treated with strong acids and strong alkalis to remove any contamination. And this was done for the samples of coal, as it was done for archaeological materials that were radiocarbon dates were accepted. Well, why weren't the radiocarbon dates for the coal accepted? You can't pick and choose. If the radiocarbon gives in the archaeological material gives a valid radiocarbon date, then the radiocarbon in the coal gives a valid radiocarbon date. You can't pick and choose. And this is from the literature. Every conventional measurement on organic material, supposedly up to 540 million years old, had detected measurable radiocarbon. So further research was done, and fossilized wood samples, for example, were chosen from various locations of various supposed geological ages up to 250 million years old. And they are all found to contain measurable radiocarbon, and therefore radiocarbon ages of only thousands of years. So, for example, fossil wood in a 189 million year old Jurassic milestone, that's a type of limestone, muddy limestone. We knew the age of the rock supposedly from the other fossils. The radiocarbon age was only 24,000 years. Here's fossil wood from a 250 million year old coal seam at Newcastle, in north of Sydney, in the east coast of Australia, had radiocarbon equivalent to a 33,700 year age. Here we have a fossil ammonite, upper right, with fossilized wood on the lower left of the sample, and from Redding, California, supposedly 112 to 120 million years old. Look at the radiocarbon ages. This is not due to contamination. These are valid AMS instrument, harsh pre-treatment, This is not contamination. This is radiocarbon intrinsic to the samples. In further research, 10 coal samples from around the US were selected from samples stored under very strictly controlled conditions by the Department of Energy at their repository at Penn State University. And these samples were of different ages, had similar amounts of radiocarbon detected in them, equivalent to radiocarbon ages of about 48,500 years. That means that these different conventional aged coals came from trees all buried at the same time, because they gave all the same radiocarbon age, so they're all alive at the same time. That's interesting. Even though they have different radiometric ages, different conventional ages, from 34 million years down to 318 million years. These are the 10 different samples from the different coal seams, different part of the US. And this is they are. The mean of these radiocarbon ages was around 48,500 years. 12 diamond samples from Africa were also analysed for radiocarbon. And all 12 diamonds contain measurable radiocarbon equivalent to radiocarbon ages of between 45 and 60,000 years, which is pushing the upper limit for radiocarbon dating, of course. And here's these samples from different parts of Africa and how much percent modern carbon was in them and the radiocarbon age equivalent. Now, this could not be due, the radiocarbon could not be due to either external or internal contamination, as these diamonds are impervious to contamination. Furthermore, the diamonds formed inside the Earth, which we'll come to in a moment. Nor could the radiocarbon have been produced by any in situ low neutron bombardment of nitrogen contained in the diamond. Now, you'll have critics who will say, "Oh, but there's tiny amounts of uranium in the diamonds." That uranium bombarded nitrogen that's found in the diamonds, and that produced the carbon-14. But the carbon-14's levels are too high for the low levels of uranium to produce the levels of radiocarbon. And that's been explained, and the critics keep on repeating this criticism, even though it's been calculated and documented in the literature that the radiocarbon could not have been produced by that mechanism. The radiocarbon is intrinsic to the diamonds. Now, these initial results were confirmed independently at the University of California Riverside Radiocarbon Laboratory. They took their own diamond samples and did their own radiocarbon analyses and published the results in the literature, and they got similar results. We need to remember that these diamonds are conventionally dated between 1 and 3 billion years. They give standard radiocarbon ages of 60,000 years. But if you look at the problems with the dating method, the corrected ages would be less than 10,000 years. We'll come to that in a moment. Remember, the diamonds formed at 100 miles down inside the Earth's mantle. At that depth, they couldn't be contaminated by the atmosphere. So the radiocarbon has to be intrinsic to the diamonds when they formed. And so radiocarbon ages that are young means that the diamonds and the Earth where the diamonds formed can only be thousands of years old. But it also means if the 10 coal samples, supposedly 34 to 318 million years old, give a young radiocarbon age, meaning they all lived and died at the same time, they all represent pre-flood plants that were buried at the beginning of the flood, only 4,500 to 5,000 years ago, means that the radiocarbon age has to be recalibrated, which we'll come to in a moment. But there are a number of ways in which the radiocarbon in a sample can be affected. We know that radiocarbon rates of production varies between the southern and northern hemisphere according to latitude. There are variations in the natural production rate affected, for example, like by the Earth's magnetic field. Human activity affects the atmospheric content of carbon-14, like letting off nuclear bombs. Fractionation effects of carbon can affect the carbon-14 production rate. Production of nitrogen-14 within trees can affect the rate of carbon in trees. Recrystallization of shells, called the marine effect. So the carbon in the shells is affected by recrystallization. Volcanic eruptions contaminating the atmosphere can affect the carbon-14 production rate. So, for example, if we look at cosmic rays coming in to the Earth that produce the carbon-14, the cosmic ray influx rate is controlled by the Earth's magnetic field. Yet we know from real-time measurements of the Earth's magnetic field over the last 200 years that the Earth's magnetic field is losing its energy so rapidly that it halves itself every 2,000 years. So 2,000 years ago, the Earth's magnetic field was stronger than today, which meant that it blocked the cosmic ray influx, which would have affected the radiocarbon production rate. If you go back 4,000 years, it would have been even worse. The radiocarbon rate, the production rate would have even been slower, would have even been less. So if you don't take that into account, so for example, that 48,500 year age for the coals is based on assuming the present rate of cosmic ray influx and radiocarbon production in the atmosphere. But back before, at the time of the flood, the field was so much stronger, the radiocarbon influx was so much less, so that gives you an inflated radiocarbon age that needs to be recalibrated. Okay, so radiocarbon ages have been actually shown to be grossly inflated back beyond about 1000 BC. The archaeologists know this. They know that archaeological samples supposedly older than 1000 BC give you older ages, radiocarbon ages that are too old from the accepted archaeological ages. So we need to be able to recalibrate carbon-14. It means, by the way, that thousands of years, real years, in thousands of real years, many millions of years of radioactive years had occurred at accelerated decay rates. While the radiocarbon was decaying at a slower rate, the other isotopes were decaying at a faster rate. So this was another indication of accelerated radioactive decay rates in the past. So what are our overall conclusions? The three crucial assumptions on which radioactive dating depends are all shown to be unsustainable, unreasonable. Inheritance and contamination in rocks are common when they are detected, which begs the question as to how sure can we be that they are not also common in rocks of unknown ages. And decay rates have been shown not to have been a constant, but have been accelerated during some past catastrophic event. Thus, all radioactive dating methods are subject to the same uncertainties. Inheritance, contamination, and non-constant decay rates make all the radioactive dating methods totally unreliable and unusable. The bottom line is that none of these dating methods is reliable, independent, or objective. Therefore, the radioactive decay methods cannot provide absolute ages for rocks and meteorites. So there you have it.
Dr. Andrew Snelling, that was an incredible presentation. I appreciate all of the work that you put into that talk, and many things I appreciate about it, but one of them is I appreciate how you would make the argument, go over the significance of the argument, and then dismantle potential objections or challenges. One example of that, and I made a lot of notes, that was great. For example, in the radiocarbon section, I find it fascinating that we find radiocarbon in basically everything in the geologic column. If I remember your slide correctly, you said more than 500 million years, supposedly, according to the conventional timeline, you find radiocarbon in these samples, diamonds, coal. And so I was thinking to myself, because I've heard many critics, I've heard them say, well, the C14 in diamonds and coal can be explained by in situ production. And obviously you heard it because you addressed it through uranium and thorium decay. And then they'll say coal, for example, acts like a carbon sponge. But correct me if I'm wrong, perhaps you can expand or reiterate the significance of those points. And the reason why I think it's important to reiterate is because I still see this argument put forth even by popular critics, like Hugh Ross, for example. I've seen him make a similar argument. And so you discussed how the numbers have been looked at and you'd need far too much nuclear material basically to recharge the C14. Is that correct?
Yes, in the diamonds, you'll see it in John Baumgartner's chapter in the second volume rate book in 2005. He did the calculation. The levels of uranium found in the diamonds, for example, you don't get enough alpha particles to impact nitrogen-14 to produce the levels of carbon-14 that we actually measured in the diamonds. And so that's agreed upon. Yes, coal, the carbon in coal, organic material, acts like a sponge for uranium. But again, you know, even the secularists know that you just don't get enough uranium to produce enough decay to bombard. You don't have enough nitrogen, for example, in coal. You don't find nitrogen in coal. You find it in diamonds, but not in coal. So how can you produce carbon-14 in coal unless you have enough nitrogen-14, which you don't have? And I might add that in the secular literature, they took samples of fossils, of coal, oil, natural gas, limestone, marble. It's all documented there in literature. It's in the rate chapter of the 2005 volume, written by John Baumgartner, and from the literature with all the references. I mean, it's there, and it's, as I said, samples up to over 500 million years supposedly old have measurable radiocarbon ages, and that means those samples are only thousands of years old. And every time a critic has raised this argument, it's been responded to. It's there on our websites, and then you get critics that will come along. They won't have read those responses, and they keep on espousing those criticisms. It's not our fault that they haven't bothered to do their homework.
Well, I like that liner. I've used that before. It's not our fault that they haven't bothered to do their homework, because like you said, these have been responded to in articles, in videos. And for example, another rescue device is what I think it is, or we can call it objection, that you addressed in the radiocarbon section of your presentation, Dr. Snelling. That's the freshest on my mind. That was the last point you covered. I was sent an article from a critic, Lorence G. Collins, I believe his name is, and he was critiquing a video of mine where I was discussing the C14 that we find in diamonds and coal and fossils and so on and so forth. And he said this, but you also debunked this in your presentation about contamination. So he said this, but many critics have said this. They're just kind of repeating the same stuff. He says, Dr. Baumgartner does not seem to realize that the instruments in the laboratories where C14 dating is done are all contaminated by modern atoms of created C14 that cannot be eliminated.
The labs take that into account. Those ages, they have a contamination factor that they built into the results that they report to you. Those ages, those radiocarbon results are minus the contamination component that the lab has calculated for their instrument. And so it's inappropriate for a critic to state that. The laboratory has already taken that into account. And so the radiocarbon result that they report is after the supposed contamination has been extracted. So in other words, they're saying this is the radiocarbon that we've detected in the sample minus the contamination factor that we've found from testing our laboratory equipment. So, this has been said time and time again, but critics like Lawrence Collins refuse to accept that.
That's very interesting. So they account for the contamination margin.
Yes,
and therefore
they report that in that analytical report. They say this is the radiocarbon result minus our laboratory our laboratory contamination factor. They don't know that, by the way, that contamination factor, they don't really know whether it's contamination or not. That's their rescuing device.
Okay.
They've tested their equipment on lots of different samples and they can't get zero radiocarbon, so they say, oh, that must be the contamination factor. But it may not be. It may be true radiocarbon. Their instrument, without any sample, gives a zero result. So why couldn't it be intrinsic radiocarbon to those samples that they tested that they claim as a contamination factor?
Well, that's a good point.
The reason they claim it's a contamination factor is that because they want a rescuing device. Because why do they want a rescuing device? Because they want the millions of years.
Right. You nailed it. Yeah, Sam, you're going to follow up, brother?
Yeah, no, I was just gonna tell you that was such a fantastic and thorough presentation. I was making, I have a list of questions, but I kept crossing them out as you were going. So unfortunately, this question might cause you to be redundant. I believe you did answer it, but it is an objection that we do get. And they'll say, okay, fine, the carbon-14 dates, they don't support the old Earth, but they certainly don't support a biblical timeline.
Well, I covered that because one of the factors that affects the production rate of carbon-14 is the cosmic ray influx.
Mm-hmm.
And the cosmic ray influx is affected by the Earth's magnetic field. So if you have a stronger magnetic field in the past, you get a lower cosmic ray influx, you get a lower carbon-14 production rate, and therefore if you use the present cosmic ray influx rate, the present production rate of carbon-14 to calculate your radiocarbon ages, you're going to get it wrong. So that's why a number of us are looking at recalibrating the radiocarbon timescale. And the way to do that is to go to places of known archaeological ages and take samples and radiocarbon date them. So, for example, we know that coal represents wood that was buried on the first day of the flood. So that means that the flood, you'd have equivalent to 48,500 radiocarbon years worth at today's influx rate, but magnetic field was so strong that has to be corrected. So 48,500 years represents the date of the flood. Okay. And then if you go to Jerusalem, you get a sample from the time of David, and that gives you 1000 BC, and that gives a radiocarbon date of 1000 BC. Great. So go to a site where Abraham was and look at the archaeological date of that. Yep. And then get a radiocarbon date. Whoa, it's a bit too high. Therefore, correct the radiocarbon date. You know how much you have to correct it by. And so if you do this for a number of samples, you get a recalibration curve, which takes into account the stronger magnetic field in the past. That would have been a lower production rate for carbon-14, which would give you inflated radiocarbon ages by, the radiocarbon laboratory that gives you the result assumes that the carbon-14 production rate has been the same back in the past when it wasn't, because you had stronger magnetic field. So does that clarify it for you?
Yeah, it does. And you answered my follow-up question too about whether or not they're starting to do that work. So thank you.
Yes, we are. And in fact, we've got archaeologists working with us and radiocarbon specialists working with us. We're connected. I did a trip to Jordan just before the COVID lockdown to look at the traditional site for Sodom and Gomorrah, potentially getting samples from there, because we know the biblical age for Sodom and Gomorrah's destruction. Therefore, if we get a radiocarbon age that's too high, we know the correction factor. We can build a recalibration curve, which is great. If we've got a recalibration curve, we can go to an archaeological site where we don't know the true archaeological age, do the radiocarbon dating, correct the radiocarbon age. That's the archaeological age.
So I guess one more question from me. So it seems like with this work that you just mentioned, that at some point you would be able to perhaps publish some predictions.
Absolutely.
Is because we hear we hear critics all the time say, well, the gold standard of science is making testable and falsifiable predictions and testing those predictions and confirming them. And they'll say Cretaceous don't do that. But from your presentation, from what you're saying here, no, Cretaceous have made many testable predictions. Many have been confirmed. For example, the helium and zircon crystals, the diffusion rate.
And I also predicted that I'd find more radiohalos where there was evidence of more hydrothermal fluids. And so, for example, I went to the Great Smoky Mountains where the Thunderhead group there, Thunderhead sandstone, as you drive over the mountain from Tennessee into Carolinas. And as you go over the mountain, the metamorphic intensity increased, and there's a location where the metamorphic reaction to produce the final rocks produced a huge amount of water. I took samples, and guess what? I predicted that the samples from where that huge amount of water was being produced, hot water, would have more polonium radiohalos, and it did. I did the same in southeastern Australia, where there were fossil-bearing sedimentary rocks that were progressively metamorphosed and then melted to form a granite. I predicted, based on where we would see the most volume of water produced at different stages of this production of metamorphism, and then the granite. And guess what? The polonium radiohalos were more of them where there was more water. And so, yes, we do make predictions, absolutely. And we test those predictions. We did that, as I showed, with the helium diffusion. We predicted, we had the two models plotted, and then we went and tested the zircon crystals, and guess what? It fitted the 6,000-year model prediction.
I love it. It really is a great time to be a biblical creationist. The helium and zircon crystals, the radiohalos, which I've learned so much about the significance of radiohalos from you, the C14 and diamonds, the discordant dates. One thing comes to mind is I've seen, and I'm curious as to your thoughts, and hopefully I can reiterate this well, but I've seen many critics, especially on YouTube, they'll argue against the data that powerfully confirms a young Earth, Dr. Snelling, with the abundance of helium being a slippery atom, the abundance of helium and known diffusion rates gives us an age of roughly 6,000 to 10,000 years, plus or minus. And they'll say, well, the rate team basically assumed relatively constant temperatures throughout Earth's history. And so if it was colder, hotter, or they made other assumptions, then we wouldn't get the evidence for a young Earth. Have you heard that criticism? And what would be a good way to respond?
Yes. Well, it's been responded to. It's been responded to by John Baumgartner and Russ Humphreys. Articles available on the website. Again, such critics haven't done their homework. Some of these critics will say, "Oh, but there's evidence of recent volcanism over there near Los Alamos in the area of the drill hole where the zircon crystals were taken from the helium diffusion experiments." But if you do the calculations, those zircon crystals, to get the results, would have to have been kept at almost 0 degrees for millions of years, which obviously is geologically totally untenable.
Right.
Nobody's said that. And that's been reported. This has been written up, and these critics refuse to read those articles and refuse to acknowledge that their arguments have been debunked.
You know, to me, and then Sam, I know you have a question on helium as well. To me, seeing that these are their challenges in rescue devices, Dr. Snelling, and how easily debunked they are, the fact that they have been debunked, but they repeat them, to me as a creationist, especially a creationist apologist, that's really encouraging.
Yeah.
Because that tells me they've got nothing better.
Yeah, it is encouraging, but also means, of course, that when we do our work, we need to do our homework as well to make sure that we've read their literature to get it right in what we're saying. And, we endeavor to do that. And so, that's why, for example, early in my presentation, I showed you examples from their literature that document the very things that I'm saying. So people can't say, it's not Dr. Snelling dreaming up that you get young potassium argon ages from young lava flow. You get old ages from young lava flows. No, it's in their own literature. You don't get inheritance and you don't get contamination, just from your claims. It's actually documented in the literature, their literature. So we do our homework.
Wow, I love it. Sam, over to you, brother.
Yeah, so I have a critic who raises a similar criticism, but it's different. So this critic suggests that the helium leakage rates that you guys used, that you came up with in your laboratory, were based off of a constant temperature. However, you compared them to the thermal vents, which have the temperature fluctuations, as you pointed out in your presentation.
How do they know it was a constant temperature? The laboratory measures the diffusion rate by raising and lowering the temperature in the laboratory on those zircon crystals. The critic who's making that claim doesn't understand how the lab measures the diffusion rate, and you can see on that graph that there were plots for different temperatures. They measured the diffusion rate at different temperatures, and they did by raising and lowering the temperature all the time and getting the amount of helium at different temperatures and calculating the diffusion rate. I mean, I'm sorry, I have to be blunt, but the person who's raising that criticism is ignorant of the actual way in which the diffusion rates were measured in that laboratory. And I might say, again, that those results came from a world-class laboratory by a leading exponent of measuring helium diffusion in his laboratory. I won't mention his name. I won't mention the laboratory. Why? Well, it's in the literature anyway, because that person got very upset when they found out that they did the work for creationists. And we had to do it that way because we know from other work we've tried to do that as soon as they find out you're a creationist, they refuse to do the work for you, even if you pay them to do the work.
Wow.
Yeah,
doesn't that show the bias in the mindset of those that reject what the Bible clearly says about the age of the earth?
Yeah, well, I had to fight a lawsuit to be able to get samples in the Grand Canyon, and it was documented as worldview bias, which is why I won the lawsuit.
Wow.
That's good.
Praise the Lord. Congratulations on that. That's for sure.
Yeah, yep. Sorry.
Oh, no, that's okay, Dr. Snelling. So again, excellent presentation. I made so many notes, but I want to skip down to the section of my notes where you discussed the discordant dates, but then you also went into Mount Vesuvius, because I see this all the time in debates, in Q&As, in videos put out by critics, and a lot of popular videos too. So I think it's a good point to emphasize. And so when you address Mount Vesuvius, you point out that they knew the target age, they got it right, but then you went into other examples where the argon to argon method didn't work. And so I'm wondering that the fact that they knew the target age, does that mean that some of the calibration that they did on their target range basically made it easier to get a correct date? Or what would be the best way to engage that if a critic brings it up, Dr. Snelling?
Well, the closer to the present is the sample, the more likely that you haven't had time for excess argon or contamination to occur. So the younger the sample, the more likely you're going to hit the target. And so it's not surprising that the argon-argon method got the target. Right, but here's the rub. Most people don't know that the argon-argon method has additional assumptions. Okay, to do the argon-argon method, they have to take a sample that is normally dated with potassium to argon dating method. And so the potassium-argon dating method relies on two measurements: a measurement of the potassium content, a measurement of the argon content. So it's easier if you can put all this together into one measurement. So what do? They zap the sample in a nuclear reactor to transform the potassium into argon of a different atomic weight. And then they measure that amount, the potassium 40 that they zap it to produce argon of a different atomic weight. And then they put that sample into the mass spectrometer to measure the ratio of those two argon. And they're assuming that all the argon derived from the potassium 40 is in their instrument to give them their result. But how do they know that the potassium 40 has all been zapped the same way? Because different nuclear reactors in different sessions have different amounts of radiation, and so they have to have what they call a flux monitor in their sample holder to do the correction factor. They put a sample of, quote, known age in with their unknown sample into the nuclear reactor, and therefore they look at how much argon was produced from potassium 40 in the sample of known age, do the calculation, and that's the correction factor for that particular session in that particular nuclear reactor. They call it the flux monitor or the fluence monitor, and they use that to calculate the argon age. Well, hello. How do they know the age of that sample that was the known age? Well, often that sample has been tested by potassium-argon dating, which has all its other problems. So in other words, there's an additional assumption that they've used. They've got a sample of known age that they use in the calculation of the argon-argon age. And so most people don't realise that. Even many geologists who are not familiar with what the geochronologists do, the geochronology community is a very small community, and most geologists out there in the field don't bother about checking how these methods work and how they're done and what the analyses are done and the correction factors and all this. They just blithely accept these results, and so do the critics, as a given, as reliable, because they come from a reliable laboratory. But underneath are all these assumptions and secondary assumptions, and argon-argon dating has that as well. And you have to have samples of known age. And so you also have to have the sample of known age that is close to the target age. What's the point of having a sample that is supposed to be 1 billion years old in your neutron flux monitor in your reactor, with a sample that's supposedly only 1,000 or so years, Vesuvius? Okay, well, it's not comparable. You've got to have a sample that you know is young in that flux monitor. And so, there's all those factors. And as I said before, the younger the sample, the less likely it has had time for excess argon or for contamination. And so it's not surprising that they got an argon-argon age that matched the Pompeii eruption. But as I showed you an example from a rock that was supposedly 500 million years old, it was supposedly 160 million years old. It was right. The argon age was right within the biotite grain, but at the edge of the grain, it was horribly wrong, because argon was migrating into the biotite crystal from between the grains, in the boundaries between the grains. And again, that was well documented. It's in the literature. The references are in our articles, our papers, technical papers. And where they got the ages wrong, they were able to explain it. So how do we know where they got the ages that they accept, whether there are factors that they haven't been able to explain that show contamination or inheritance, etc.?
That's really good, because then it makes me wonder if a lot of these scientists are just assuming that the dates derived are accurate. They're not really looking into it. They don't know the details, for example, of what you were saying with the argon to argon method. Are they then aware of all the discordant dates, all the wrong dates that they're getting, all the problems with that? Do you think, Dr. Snelling?
No, usually not. I mean, it tends to be a small number of dates that are discordant, but then it's because they don't usually use more than one method on the same rock sample.
Right.
And where they have been discordant dates, like I showed you from that South African sample. They actually did multiple methods on the same granites, and they got and different minerals in that same granite, and they got ages from 5 billion years down to 2 billion years. And so, that was a sample in Africa where they used multiple methods on the same granite rock. And so it has been done in the literature, but very rarely. And so the general geochronology community isn't even aware of these problems because they don't test for these problems. They assume the methods work. They give them the results they want. The results are in the correct order in the geological record, but there may be a systematic reason why they're in the correct order. Yes, accelerated nuclear decay would give a systematic pattern in the rock record, as I explained.
Yeah, because I took a bunch of pictures of your slides, and once we air this live, it'll be easier to look at your slides in more detail. And you had a couple here that were fascinating, and they relate to what you were saying here, Dr. Snelling. For example, one slide here, Cardenas basalt,
yes,
lavas. And then you asked the question, a good question, which date is the correct age for this rock? The isochron age, and then the method. So potassium, argon, rubidium, strontium, different ages, 516 million years, 1,111 million years, 1,500 years, which is 3 times the amount the potassium. So is that what you're saying, that you can use, as you and the RATE team have, different methods on the same rocks, and you're getting totally different ages for them?
Correct. Yes. On all four rock units that we targeted, we got different results for the different methods. And there was a systematic pattern in those results. Potassium or rubidium were always the youngest. Potassium was always younger than rubidium, and rubidium was always younger than samarium or uranium. And so there was this pattern that could be correlated to the atomic weight, the beta decay versus alpha decay, and also the rate of the decay rate of the parent atom. The larger the atom, the slower the decay rate, meant that the larger the atom, the faster the accelerated decay would have to be, the older age for uranium versus the rubidium or the potassium. And so when you get a systematic pattern like that, it means there was a systematic process involved.
That's really good, Dr. I want to ask this question, then Sam, I'm going to throw it to you. And so that was really interesting to me, whereas secular geologists, non-young earth creationists, might struggle with those different ages derived from different methods. But if I understood what you just said correctly, and also what you presented correctly, accelerated decay would act differently depending on what the parent isotope is. And so that's why you'd get different rates of the accelerated decay, and therefore different numbers.
Yeah, you've got the lava flow erupted and it cooled, and that was at some time, real time in the past. So there is a real time period from the formation of that Cardenas basalt and the present. In that real time period, the potassium argon clock ticked through 516 million years. In that same real time period, the rubidium strontium clock ticked through 1111 million years. And that real time period, the samarium neodymium clock ticked through 1588 million years. And so the samarium clock ticked 3 times faster than the potassium clock. And so that's how you can tell. You can only reconcile those ages because there was only one real time period It meant the clocks ticked at different faster rates in the past.
That's a really good point. And Sam, I'll throw it to you first, and then go ahead, brother.
Oh no, I mean, if you had something that you wanted to respond with that.
Well, I guess I was just curious in light of what you're saying, Dr. Snelling, which is some really good information. That's great material. The necessity of accelerated nuclear decay based on what you presented with the radiohalos and then the lava flows, I guess, these volcanic eruptions, and then the subsequent hardening of the rock would be taking place during the flood. So is that why? Because some creationists might say, well, there were accelerated processes during creation because God could have created rocks with ratios, uranium, lead, a ratio of them, pre-existing atoms, which makes sense. But then you also need accelerated decay during the flood and not just at creation, because the rocks that we're finding these dates in are from the flood, basically.
Correct. Yes.
Okay.
So, for example, I wanted to check whether this was actually due to physical radioactive decay, because some people could say, oh, the numbers are just chemical analyses. Did real decay occur from uranium to produce that amount of lead? So the radiohalos are evidence that physical decay did occur. Another product of decay is another process of decay is fission, where a uranium atom splits, and so you get fission tracks in zircon grains in volcanic rocks. And so I looked at different levels in the geological record in the Colorado Plateau, and I looked at volcanic ash bed in the near the bottom in the Cambrian, supposedly 500 million years old, and it had 500 million years worth of fission tracks. I looked at a sample from the Morrison Formation in the Jurassic, about 165 million years old, conventionally wisdom, and it had fission tracks equivalent to 165 million years of fission, nuclear fission. And then I went to a lava flow around in Arizona, northern Arizona, in near the name of the town escapes, the city escapes me, on the I-40, and that had a million years worth, and that's the conventional age for that lava flow. And so that means that during the flood, because the first layer was formed during the flood, there was the 500 million years worth of accelerated fission track actual nuclear decay that occurred. And the same with the radiohalos. And so this wasn't just an artifact of geochemistry, this was actually physical decay having occurred during the flood.
That's a really good clarification. I'll say this as a follow-up, then Sam, we're going to throw it to you. So many questions we could ask you, Dr. Snelling. This is great. And so the fission tracks point, that's an important point. That really helps me understand why accelerated decay was required, but we also have the evidence for accelerated decay during the flood. And so the fission tracks, when basically the uranium atoms split, you're left with this marking or this track. And so it's interesting that when you looked in the Cambrian, you said, which conventionally would be dated 500 million years, you have 500 million years worth of fission tracks. And then I think in the Jurassic is what you said, roughly 150 to 160 million years, conventional dating wise, you have that amount of fission tracks and so on and so forth. And so all of that would have taken place though during the flood, because those are rocks.
That's right.
In the flood, right? Flood rocks.
Yeah, the rock at the bottom formed in the beginning of the flood had more time for more atoms to fission than the rock formed higher in the flood. It had less time during accelerated decay, accelerated fission to occur in the latter part of the flood. So you'd have this systematic at different levels in the flood layers. You'd have different amounts of accelerated nuclear decay, giving more amounts of products, daughter products, fission tracks, radiohalos, etc., to be available. So you don't find radiohalos in very young granites, for example. There just wasn't enough accelerated nuclear decay to produce dark radiohalos.
I appreciate that. Sam, over to you, brother.
Yeah, so about the radiohalos, you did a fantastic job explaining that. Thank you. That's a complicated thing, and your slides made it very well. So you showed that they had to form fast, and then you said that that heat would have destroyed them. So the process couldn't have created a lot of heat. But would you say that the formation of the halos did create heat, but there must have been a way for it to dissipate? Is that what you're saying?
Yes, and heat. There's interesting studies. I did studies on the formation of granites, because granites usually supposedly take millions of years to form, to cool. I'm doing studies on metamorphism, and I look at stuff in the results in the secular literature as well. And the point is that the water to form the radiohalos is only released in the granite at 373 degrees C. Everyone agrees on that point. But unless the granite cools rapidly enough, and those fluids cool rapidly enough, they will have stripped out all the uranium, the polonium being produced by the uranium. So, in other words, the temperature's got to drop quickly enough, and the fluids have got to cool quickly enough, below 150 degrees, for the radiohalos to start forming. And the same with the metamorphism. The metamorphism produces fluids, but fluids are also involved in the metamorphism at a rapid rate. And so that means that the temperatures have to drop very quickly. And part of to eventually get to below 150 degrees to actually generate the radiohalos. And then if it cools too quickly, the fluids, of course, get slower and slower because they don't have the energy to move. So they're not moving the polonium. And so the radiohalos don't form. And so you've only got a very narrow time window for granites to form and to drop from formation to polonium radiohalos. Otherwise, you wouldn't get them in the rock. So that was an indicator that granites form rapidly. But it means that there has to be another process that is sucking out the heat. And one of those processes is water, because water moving will dissipate heat. You've got water in the flood. You've got water in the pre-flood oceans that is cooling water that's being generated by volcanic and granite and metamorphism, etc. Water coming from inside the earth that's hot, that's being mixing with hot, cooler waters, pre-flood waters. So that's going to have an effect. In fact, the hot waters coming up from the fountains of the Great Deep have lots of chemicals from the mantle. When they hit the cool ocean waters, those chemicals are going to precipitate, which is why you get lime and you've got salt beds that most people claim take millions of years to form, of evaporation and all that sort of. And so it's a side issue, but it's relevant. And the same with waters being flushed through rocks, they're going to dissipate heat. It's a very effective way. But there may also have been other factors going on, and Russ Humphries has been delving into that. There might have been other factors that we're unaware of that would suck out the heat. My concern is that the data, that is the observable radiohalos, survived, means that they had to form below 150 degrees while there was accelerated radioactive decay still going on. So that radioactive decay, accelerated radioactive decay, couldn't have been producing enough heat to wipe out those radiohalos.
Yeah, that's a fantastic answer. At the end of the day, they're there. And so they had to form fast. And because they're there, the heat had to be dealt with, whether we can explain it at this time or not.
And it's the same for the fission tracks. The fission tracks are also wiped out if the rock rises in temperature.
What's the secular explanation for the radiohalos?
Well, G. Brent Dalrymple on the witness stand at the Arkansas trial in 1909 said it was a very tiny mystery. And the only person who has really critiqued the radiohalos is, again, Lawrence Collins. And he tries to tell you that it's because I got it wrong about why granites form. They form by a different process called metasomatism. But he fails to mention that the features he refers to myrmekites aren't recognised in all the granites and they're not in many of the granites that I looked at. And the secular community ignores or doesn't appreciate or doesn't recognise his methodology for explaining granites. It produces hot water anyway, and he's not explaining why you got polonium radiohalos in schists in metamorphic rocks. Myrmekites don't form in metamorphic rocks. He's just ignoring. He's just selective in some of the data he used. He claims that it's radon. But wait a minute, if they were radon halos, radon is an inert gas. Radon will not be geochemically concentrated in any one location because it's geochemically inert. Polonium is chemically active. It has the same valence as lead. And so it's geochemical. And I looked this up. There's a volume published in 1957 on the geochemistry of the rare elements. And you can look up polonium and it's got all the geochemical details. And it was a eureka moment when I found that in the University of California, San Diego Library on a Sunday afternoon at over there in San Diego area. And suddenly I saw the connection. Polonium connects with sulfur, connects with chlorine, and that's can sit between the biotite crystal flakes in the cleavage planes where the hydrothermal fluids are being transported. Radon won't do that. It's geochemically inert. So you can't have radon radiohalos. They don't exist. Nobody's ever recognised them. And Lawrence Collins will say, oh, but you misidentified the halos. They're really radon halos. No, I didn't misidentify them. Robert Gentry identified them based on 1, 2, and 3 rings that equates to the energy levels produced by bombardment by alpha particles of energy parented by 218, 214, and 210 polonium. End of argument.
So a lot of good points there. You remain unpersuaded, or would you say that the best arguments, and I'm not even saying they're good arguments, that critics like Lorence G. Collins are offering, they're not very persuasive in actually addressing the data of radio halos, Dr. Snelling?
All the data. You can select things, and but you haven't taken into account the total picture, the geochemistry of the rocks, the fluids, what rocks, where, schists, metamorphic rocks, as well as granites, where you've got more hydrothermal fluids, you're getting more radiohalos. All those things, all those factors he's not taking into account.
So in light of all that, then, those are some very important points. Going back to this issue of, well, the global flood and accelerated decay, Dr. Snelling, would have released far too much heat. It would have cooked the planet. It would have killed Noah and the ark animals and so on and so forth. But the presence of radiohalos, which is powerful evidence for accelerated processes like accelerated decay, the best the critics have had to offer don't work. The argument from radiohalos and fission tracks and everything in combination, obviously the helium and zircon crystals, powerfully suggest accelerated decay. But at the same time, with what you're saying now and then in your presentation, at pretty lower temperatures, those radiohalos are obliterated, which means, okay, the heat that was released must have been dealt with. There wasn't a heat problem, or else those radiohalos wouldn't be there in the first place.
Correct. There must have been some systematic mechanism for that heat being absorbed or released. And we haven't discovered that yet.
But we know that accelerated decay happened because of the radiohalo. So I find it interesting because the critics are kind of in a tough spot then.
Correct.
They can't address the radiohalos, but then they keep, it's almost like they're dodging the evidence from radiohalos and just moving to the heat. Well, we don't know how to address the radiohalos, but what about the heat? You know, it kind of seems like they're moving the goalposts, or they're dodging in a way.
Well, it's the same. They ignore the anomalies because they want to focus on what fits their narrative. We could do the same thing. That's why we have to be careful we do our homework. But that's right. They're focusing on little bits and pieces and not looking at the overall picture. And just because we haven't got an explanation for something doesn't mean there isn't an explanation. They do the same thing. You know, as a friend of mine often says, the absence of evidence isn't evidence of absence.
That's right.
I mean, we find the coelacanth fish fossil at 66 million years, supposed rocks. We don't find it buried in rocks younger than 65 million years old, and yet we find it alive today. Does that mean it died out? No. It was alive for that period of time, but didn't leave any fossil evidence. So the absence of evidence doesn't mean evidence of absence.
It's an excellent.
Same with the Wollemi pine. You know, it's
right.
They call them Lazarus fossils.
It's like finding a living dinosaur. I've heard them say.
Correct. Correct. Well, that's why the Wollemi pine was called the dinosaur tree.
Right. That's great. So it's a great point with the coelacanth too. And this is kind of another topic, but it just brings to mind because they'll say, well, how come the ordering of the fossil record from more simple to complex evolutionary progression, so on and so forth, from Precambrian to Cambrian to today. But I understand there's post-flood rocks too. But then the coelacanth, they say went extinct for roughly 65 million years because it disappears in the rock record. Yet we find it today swimming around in the oceans, coexisting with animals like dolphins and whales. And yet we don't find dolphins, whales, coelacanths, and humans buried together. So it isn't. So the evolutionists has the same problem when they want to ask, well, why don't we find
correct
humans and dinosaurs buried together, and all those questions, Dr. Snelling?
Yes, it is. It's the same problem for them. And by the way, more and more we're finding that you're getting more and more vertebrates, for example, found in the Cambrian. In fact, the problem for the evolutionists is the Cambrian explosion. Stephen Gould didn't have an adequate answer to that suddenly you go from microscopic, single-celled and, multicellular organisms, suddenly you get all the major body plans, all the phyla suddenly represented in the Cambrian. Even vertebrates are recognised in the Cambrian. You used to say that fish only appeared in the rock record until you got up towards the Silurian and Devonian, but now they've found fish down in the Ordovician and evidence of fish down in the Cambrian. So more and more, this so-called explanation or scenario of simple to complex from invertebrate to vertebrate is being demolished by their own evidence of finding more and more of these fossils. And again, just because we don't find lots of fish fossils in the Cambrian doesn't mean that fish weren't around swimming. They just didn't get buried at that time. The flood was a progressive burial event. The fountains of the Great Deep broke open. The Great Deep is the oceans. So the ocean floor would be first affected. What creatures would you first expect to find fossilized in the fossil record? Ocean floor dwelling creatures. What do we find in the fossil record? Trilobites, corals, clams, ocean floor dwelling creatures. So only as the floodwaters climb higher and higher, demolishing more and more pre-flood ecosystems, do we find those ecosystems swept away and buried in the fossil record? Still, by the way, with seafloor dwelling creatures. And I might add, where do we find all these seafloor dwelling creatures buried today? We find them buried on continental rocks up on the continents. How did creatures that lived on the ocean floor before the flood get buried up on the continents? Only a flood that started in the oceans would pick them up and bury them up on the continents. We find the dinosaur fossils buried up on the continents. And we also find marine fossils buried with the dinosaurs. So let's get the complete picture. Let's not cherry pick which fossils are found in which layers.
Right.
We find marine fossils all the way through the whole record.
Let's look at the general pattern rather than just picking up certain, like as Bill Nye the Science Guy says, we should find a rabbit in the Cambrian, for example. And so the bigger picture, the general pattern is so important. And the pattern of going back to the dating methods, Dr. Snelling, because the ultimate question that I see from critics, which you've answered in a comprehensive manner, is why do rocks lower in the geologic column date older than rocks at the top? But like you said, and correct me if I'm wrong, the way I understood it is, well, we can take those dates as relative dates, not absolute dates. And so you'd have more hits of accelerated decay.
Right. The rock lower in the record has had more time for accelerated nuclear decay to occur, so it has more decay products, so it gives an older age.
Right. That's great. And we've got excellent evidence for accelerated decay happening. And so this question here, as we start to wind down, it's been so thorough and so informative, Dr. Snelling. I appreciate this. And it's important that we engage critics and we address challenges like this. And so this is very helpful. And so you addressed this early on in your presentation, but it is a commonly repeated criticism. I see it brought up in nearly every debate on the topic, and there's popular videos that essentially claim that the rate team, which you were part of course, use an inappropriate method, potassium to argon dating. But then in your slide, you showed where conventional scientists use the same dating method anyways, for dating very young rocks. And so that's kind of their rescue device to explain why we get newly formed rocks. We know when they were formed, but yet they date incorrectly. And they're saying that the method used is the wrong method. What is the best way to address that, Dr. Snelling?
Well, if you look at the pattern of criticisms, is when they can't debunk the methodology, they'll debunk the scientists. They'll make the attack personal. And so they'll say, oh, well, Steve Austin didn't take into account xenoliths. That is foreign rock material that was caught up in the passage of the lava, the volcanic rock, in the mouth of the Mount St. Helens eruption. Well, hello, the same scientists who make those claims didn't do the same checks themselves in their own rock. I mean, it's the pot calling the kettle black. It's not, and they routinely use these methods on rocks of all types, of all different ages. They just select the method which they have access to the equipment that they feel is the most appropriate. And today, the most appropriate method they want to use is uranium lead, because they know that there are problems with those other methods. In fact, the interesting thing is I did a series of technical papers where I explored how were the decay half-lives of these isotopes measured. And, you know, did they physically in the laboratory put a Geiger counter there and measure how many decays over a certain period? Yes, they did that. But they couldn't do that for all the different methods. They had to find ways to deal with discrepancies, because after all, they only did it for a few years. And you know what? They ended up calibrating potassium, rubidium, and samarium half-lives, lutetium, hafnium, rhenium, osmium. All those were calibrated against uranium. They took samples with known uranium dates, and they calculated the dates by those other methods in each instance separately, using the half-life. And when they found that there was a discrepancy, so for example, they took a lava flow on the shores of Lake Superior, and the uranium lead date for uranium from zircon gave an age of 1.1 billion years, but the potassium age from one of the feldspars gave a different age, slightly different age. So what did they do? They recalibrated the potassium decay rate in that sample to match to get the correct potassium argon age. Wow. In other words, they calibrated the potassium decay rate against the uranium decay rate. So all the other methods have been calibrated against uranium. And then if you go to the determinations of the uranium decay rates, there's some discrepancies there as well. So they're not totally accurately known. And those papers are available, again, on our website. I've done all that homework to show how they ultimately calibrated all the other methods against uranium.
Wow, that's interesting. I also found it fascinating during your talk, closer to the beginning, or all throughout, but I made a lot of notes here. For example, closer to the beginning, you talked about the 10 diamonds that yielded an age of 6 billion years, which is kind of a problem if the Earth, according to secular scientists, is only 4.5 billion years old. And you went over plenty of other examples, though, but showing obviously that all of the assumptions behind dating methods have been falsified.
Yeah, well, in that particular case, of course, they knew that they got the wrong result.
Right.
So in subsequent studies, they studied the diamonds more carefully. They found fluid inclusions, and those fluid inclusions had nitrogen and also extra argon. And so they knew that the argon was excess argon incorporated in the fluid inclusions in the diamonds when they formed. And so they used that as their explanation. So again, when they know the true age, they know there's a problem. So how do they know the true age of an unknown rock sample? They don't. They're assuming that they're getting the correct result from their dating method because it fits what they want.
Yeah, they beg the question.
Mm-hmm. Exactly.
Right. As you put it in your presentation, you said if these assumptions are violated from recent lava flows, and we know the ages for the origin of these rocks, why should we trust ages derived from rocks in the unobserved distant past?
That's right. And that's why I showed you the example from the Grand Canyon. The youngest lava flow gives the same rubidium strontium age as the oldest lava flow. So if the youngest lava flow inherited its rubidium strontium chemistry from its source, then the ancient lava flow that came from the same source must have also inherited its rubidium strontium chemistry from that upper mantle source. Mm-hmm. So its rubidium strontium isochron age isn't a true age either.
Wow.
Yeah, it seems there's a huge problem, a contradiction, I would say, between their assumption of uniformity and their explanation of the geological column, because they would say that each stratigraphical layer is the result of certain environmental pressures, and then those pressures change, whatever creatures in there died off, and that's what caused that layer to be distinct from the layer above and below. And so, if that's true, if their interpretation of the geological column is true, then uniformity would be false. But if uniformity is true, then it seems like their interpretation of the geological column would be false. What do you think?
Well, you've certainly got a stack of layers. I mean, there are physical layers, so it's really the time interpretation based on other factors, either radioactive decay, sedimentation rates, fossil content, etc. And so you get problems with their methodology. So, for example, in the Grand Canyon, you've got a sandstone and below it's a siltstone, and you go 50, 70 miles away, you find the same sandstone on top of the same siltstone, but between them is another rock layer. So they say, well, that rock layer in between must have taken millions of years to form. That means up there in the Grand Canyon, there must be millions of years missing at the boundary between the sandstone and the siltstone. But you don't see any evidence of the millions of years. It's a nice flat boundary. There's no erosion that you'd expect from those millions of years. And so you get all these discrepancies that they try to gloss over or ignore.
Dr. Snelling, it's somewhat off topic, but someone from our team really wanted to ask you about, because, well, we all find the cold slabs that you find deep within the earth that meet catastrophic plate tectonics expectations. And I've seen you speak on this. We've had Dr. John Baumgartner on for a seminar. He spoke on it, of course. As creationists, should we argue that the cold slabs are a fulfilled prediction or expectation, or what's the best way to approach that?
Absolutely. John Baumgartner predicted that because catastrophic plate tectonics was rapid and it was recent, then the pre-floodation floor slabs that sank down to near the core mantle boundary would still be cold. There would not have been enough time since the flood for those to homogenize in the mantle. So he predicted that they would be found, and a few years later they were. So that's a fulfilled prediction, yes.
Does that date us to these massive slabs of cool rock that should have either assimilated, from my understanding, to the surrounding material, or even melted if they were taken down there millions of years ago? Does that still baffle the secular community, do you think, Dr. Snelling?
Yes, it does. It still baffles them.
Wow, that's awesome. Okay, one other point too, Mount Doom. As a Lord of the Rings fan, I appreciate that you mentioned Mount Doom, and I never thought that Lord of the Rings would help us refute the billions of years paradigm.
It was filmed in New Zealand. You can actually go to Hobbit Town.
Yeah, I'd love to. That's on my bucket list. I have to. Okay, well, Sam, unless you had any final questions, this has been comprehensive. 3 hours flew by. Dr. Snelling, you have great endurance because that was a very thorough and informative presentation.
Yes, it was.
I appreciate the way that you constructed it. Again, you'd lay out the argument. You'd bring up objections, you'd refute those objections. And so I would consider that a very up-to-date lecture dismantling dating methods, including isochron, which is important because critics do like to bring up isochron dating to counter the built-in assumptions, but you dealt with that adequately. And so, Sam, any final questions, final comments as we start to wind things down?
Yeah, I just want to thank you both for letting me spend my evening with you. Dr. Snelling, you made this interview difficult for me because you were so thorough. You didn't leave any meat on the bone for me. So,
well, I'm aware of what the critics are saying. That's the point.
Right. I appreciate that very much because we also do. We engage with a lot of critics here. So very much appreciate somebody who understands their mindset and their arguments and refutes them as they go. So thank you very much for that. Thank you for your time.
It's a pleasure. Glad to help. That's what I'm here for.
I appreciate that. This has been a real privilege and an honor. Dr. Andrew Snelling, you've done so much in terms of upholding the truth of biblical creation and biblical Christianity in general. And so I hope that this program is valuable and helpful to those that watch it. I want to encourage you to share this around to your friends, your family, share it around on social media, and pass it around to the critics in case they bring up an argument, challenge, or objection that may have been addressed here in this program. Dr. Snelling, God bless you. Thank you for joining us.
Thank you. Pleasure. Glad to help.
Okay. Standing for Truth is signing off. God bless all.